Alright, you guys, so for this first one, we have that our good old friend Billy is what they call a keen walker, who keeps a record of his performance so that someone can do a math problem at some point. Anyways, the following table shows the time in minutes it takes for him to walk 1 kilometer up hills with different gradients, okay? The gradient of each hill is constant. So first things first, I'm sure some of you are already thinking, damn, I do not know what gradient is. Gradient is a synonym for what they call slope, okay? You can also, or you might have heard it as what they refer to rate of change, right? Usually I hear gradient or slope, rate of change is a little bit more weird, so we're gonna stick with the first two, okay? Um, And if you put this into your formula booklet, if you look for gradient, here it is. As you can see, it is m. And so gradient or slope is the famous m. And the formula is y2 minus y1 over x2 minus x1. What does y2, y1, and x2 mean? It makes reference to a set of points. So x1, y1 or x2, y2. And so it's your first x with your first y, or your second x with your second y. Okay, it's just sets of points. All right. And as you can see, the y's are on top and the x's are on the bottom. So you can think about it this way. Basically, if you take a line, okay, the slope or the gradient is going to be how much you move by x, which is, the difference between x2 and x1, right? This is my denominator. And also by how much it rises, right? So here's going to be your y1, here's going to be your y2. And so as you can see, this here is exactly x2 minus x1, and this here is exactly y2 minus y1, okay? This is also why in some of your schools, it may have been taught to you as rise over run. How much you rise divided by how much you run in your graph, okay? And so in this case, you actually have a slope that is positive, okay? If you have something that cuts, like downwards, it's going to be negative, okay? If you have something that cuts straight across, it's going to be a slope equal to 0 because you're rising 0, right? But you're running something. So 0 divided by anything is going to be 0. And you also have the case where it's what they call undefined, which is just a line, a vertical line. This is going to be undefined because you're going to have some rise divided by 0. And anything divided by 0 is always going to be, ladies and gentlemen, undefined. Okay? So vertical slopes, undefined. When they're flat, they're equal to 0. And yada, yada, yada. See? Anyways, that's a little bit of blah blah for us to discover what gradient is. Then they tell us that the gradient of each hill is constant. Now let's understand what constant means for a second. So constant means that it's constant. It means that it doesn't change. Okay? And so here, Billy, our good old friend Billy, he recorded this table, he sent it to his math teacher, and his math teacher did an IBAISL November paper. Okay. And so, thank you, Billy. Thank you. Point is, when it's a constant gradient and we're talking about a hill, that means that what Billy is doing is that he goes up a hill and he considers the gradient constant. Okay? That means that the gradient doesn't change. It means that the slope doesn't change. And so, in some cases, he has a slope of what he says is 10%. In other cases, he has a slope of what he says is 4%, which is, of course, a little bit lower. Okay? And so that is what Billy's doing. He's saying, yo, this is a hill. The hill looks like this. It's constant. Okay? That's going to be relevant for part C. For now, we don't really care about that, but the context is very important. Okay, so that is what's happening. This is what's going on. And here is my table. All right. So at a gradient of 0, he takes a little less than 7 minutes to finish. At a gradient of 4%, he takes a little less than 9 minutes to finish. Okay, etc., etc. So for part A, part I, it says to find the equation of the regression line of t on g. Now, I need you guys to do the following. The moment you read regression line, you're going to be thinking graphing calculator, okay? Maybe you don't remember well where, maybe you're not so sure how it works, but you know that you have to use your calculator, okay? And so a big part of AISL, to my liking, is just understanding how the heck your calculator works and all the stuff it can do, okay? And so let's understand first what a regression line even is. So let's say you have a scatter plot with these points, okay? Whatever, it's a little spread out, who cares? See? Point is, someone shows up to you and they tell you, okay, what's like the average here, right? And so what you would do is that you would just kind of like try to trace a line that goes like in the middle of all of them, okay? That is your intuition for a regression line, okay? It takes all your different points of data, it tries to find sort of like a mean, okay? Something that cuts through the middle of most of them. And sure, there's going to be a little bit of spread here, a little bit of spread there. But point is, it's a regression line that can help you, I don't know, predict or understand better your data, okay? And so how do you find this regression line with your graphing calculator? Okay, the moment you read regression line, you're going to be thinking calculator, okay? And I'm going to show you when and where and how it works. See? The second thing is that here it says of T on G. Now, I'm sure a lot of you are reading that and thinking, what the heck is T on G? And first, I'm going to give you like the general form, okay? So the general form is regression line of y on x. So what that means is that you are trying to like see the values of y depending on what you got for x. Okay, that is huge. I actually said it in such a beautiful way. You are getting the values of y depending on x. So y depends on x. So now you can even say that y is dependent variable and x is independent variable. Independent variable. Okay. And so notice how in this general sort of form, y is the first one, x is the second. And so if you remember that, well, this t is going to be your y, this g is going to be your x. So that means that this is your x values, and these are going to be your y values. And so depending on the gradient, how much time does it take to climb up that hill? Or to walk 1 kilometer up that hill, better said. Anyways, once you consider that, it's a little bit easier to, see what you have to do or whatever, all right? So regression line, you're going to pull up your calculator. You are calculating some sort of statistical thing. So you go to stat, you go to calc to remember better where it is. And then you say, there it is, line reg, regression line, line reg, whatever. It's the same thing. Okay, linear regression, regression line, yada, yada, tomato, tomato. So you press here and you see what it asks for. As you can see, it's got an X list, it's got a Y list, it's got a frequency list, and it's got a store reg EQ. Now, it's important to think about it this way so that you remember what you have to do. So you press calc, you reach line reg, and you see that it asks for lists. So now you gotta go back to stats, go to edit, and edit those lists. So you're gonna erase both, and now you're gonna put the according ones here. See? And so I said that x was gradient, I said that y was time, so I'm gonna say that the x is gonna be L1 and the y is gonna be L2. Okay? Technically you can flip it, but I suggest that L1 is always gonna be x. Okay, just do it the same way always. X is gonna be L1. So you clear your lists, you put everything in. So this L1 is going to be by x, which is gradient. And this L2 is going to be time, which is a very interesting concept created by mankind. I just find it so powerful. The concept of time. I think it's one of the stronger concepts we've ever created. It's very impressive. Anyways, back to math. So you can go to stat, you can go to calc, and now you can do line reg. See? Now make sure that your X list is L1, or the one you chose. See? So to put L1, You see that blue button here on top of 1? So you press the blue button, you press 1, kapow! X list L1, Y list L2, and here you have frequency list. Guys, do you have a frequency list? No. I feel like a lot of you stress out and feel like you have to plug something in always if the calculator has it. You don't have to always do it, okay? And that has to do with feeling familiar with your tools, feeling familiar with your graphing calculator, okay? The day of the test, you're going to walk in with few things, okay? You're going to walk in with a pen and pencil. You're going to walk in with 2 years of having learned the world of IB math in your wonderful school, and you're going to have 2 hours of sleep, okay? What else are you going to have? You're going to have your formal booklet, so make sure you know damn well what's in here, okay? Always study with it. And you're going to have your graphing calculator. Okay, so the graphing calculator, you gotta know how this thing works because it's a tool that you're gonna use the day of the test. So always use it, learn it well. Frequency list, if you don't have one, you don't plug it in. See, some people here like freak out. They think they have to put something, so they just put L1 and sorry, yeah, they put like L1 or L2 or whatever, and chaos ensues. Okay, you don't always have to put something. Forget about it. Okay. Yeah, so frequency list, you're going to leave it literally empty. And here you have store reg EQ. So let's remember that this linear regression function thing is going to give you literally a line. And so if you want to graph this line for some reason, you can actually press alpha trace and you can put into any one of these. See? Now what are these y1s, y2s, y etc's? It's in your y equals, okay? And so if you want to be a cool kid, you can put it in here, graph it, and look at it. Technically, you don't have to. I mean, for what we care about, you don't have to. If you want to be a cool kid, you can, but whatever. See? Yeah. And then you press calculate. So you press calculate, you get all of this stuff. See? Wabam. Now I'm sure at least one of you out there, and this is for you, my guy or girl or whatever. I'm sure at least one of you is looking at this and saying, dude, I did not get an R value. Why is this guy in YouTube getting values for A and B and also R, and I'm only getting values for A and B? That happens because you didn't say wablam loud enough. Okay, you gotta say wablam. What you actually have to do is press mode, okay, scroll all the way down, and there's this thing called stat diagnostics. You're gonna have this guy always on. There's no reason to have it on off, because if you have it on off and you do the same thing that I just did, you're gonna find out that when you calculate and you say wablam, you don't get R. See? You don't get R, even though it's the same process. So make sure this thing in mode is always on. There's no reason to have it off. It's only gonna maybe confuse you a little. See? So make sure that is on. Press calculate. Here are my values. Okay? So that was a lot of blah blah, but I think it helped more than one person out there. See? Anyways, for part AI, let me just write it over here so that we're all on the same page. You have, for finding the equation, right? Here it is. You have y equals your A value, which is 0.55213x, plus your B, which is 6.3570, 6.3570, and there it is. Okay? Technically, if you want to do significant figures, you count, for significant figures, you would count from here 1, 2, 3, skip the 0, okay? And this one, do you round it up or down? I mean, do you round it up or keep it the same? You keep it the same. So the first one, if you would like, you can leave it as 0.52x plus, count 1, 2, 3. Do you round it up or keep it the same? You round it up, so you can leave it as 6.36, okay? So with significant figures, if you really want to, and just to keep it all in the same color, it would be 0.522x plus 6.36. Now, I did put y and x here, right? Now, because of context, which is y, which one is x, we said earlier that y is t, that g is x. So I'm just going to replace that quickly. You're going to end up with g. T is y, my bad. So you're going to have t equals 0.522 G. All right. So just to follow through with the context, that's what it would be. For part A double I mean, that's part A, part A. For part A double I, we have to describe the correlation between T and G with reference to the value of R, the Pearson's product moment correlation coefficient. So this is probably the longest buzzword you're ever going to have to learn for any test. Okay, so the moment you read this, you have to think line reg. All right, now that's something we already did. And as you noticed in our results, you have an R value. Okay, but if they ever don't tell you the regression line and they tell you about Pearson's product moment correlation coefficient, you got to go into line reg. Okay, so this is another big buzzword. Don't be scared. You just got to do line reg. And it helps you find the correlation, right? And so what I explained earlier, where you drew like the line that goes in between all of them, what this is trying to find is the correlation between your data. Now, what is a strong correlation? What is a weak correlation? Usually, think about an R equals 1 as a strong correlation. Okay, actually, equals 1 is a perfect correlation. So perfect correlation is equal to 1. Okay, and so anything near that is going to be strong. Equal to 0 is trash. Okay, or just not perfect, or opposite of perfect, whatever that is. See? So anywhere near to 1, you would say that it's a very strong positive correlation. See, if it's negative, then you would start saying it's a negative correlation, stuff like that. Okay? Anyways, so for this one, our R value was, or is, 0.9939. 0.9939. If you count 3 significant figures, it's going to be 0.994. Now, as I said, this is very close to 1, so you can call this a very strong positive linear correlation. Okay? The bigger buzzwords you have to say is strong, positive correlation. Okay? I think with this, you would probably get full credit. All right? Strong positive correlation. With that, you're fine. And if you want to like make sure you get the right answer, like 100%, you would say strong positive correlation because R close to 1. Okay? Or whatever. See? As long as you point out that you got the R value, it'll be okay. Yeah. So that is part A, part double I. Then they tell us that on Sunday, Billy intends to walk up a hill with a gradient of 13%. And so we need to estimate the time it will take Billy to walk 1 kilometer up the hill. Now this is pretty standard, but you have to really be careful on what is X, what is Y, and substitute correctly. So basically, in other words, for part B, what we're getting handed to us is that our good old friend Billy has a gradient. He knows he's going to go up a hill with a gradient of 13%. How much does he take? And so if you really translate this a lot, you would say G equals 13. What is T? All right. And if you want to put this as a set of points, remember that G is your X. So it's going to be 13 comma Y. All right. So, well, and in this case, it would be 13 comma T because T is Y. And so if you go ahead and plug that in, it would look like this. 0.522 times your G, which is 13, plus 6.36 is going to equal T. So you put all of this into your calculator. 0.522 times 13 plus 6.36, you get a T value of 13.146. T equals 13.146. And give me a moment. 0.522. Wait, give me a moment. Something is wrong here. Okay. I think this is what's wrong. Apologies for anyone watching this. Your A value, I hope you saw it earlier, but the A value I wrote down is wrong. So it should have been 552 instead of 522. So my bad. If you saw it, nice. If you didn't, it's okay. We all make mistakes. No one's perfect. And I'm glad I'm another example of that. So, yeah. So here you would have to plug in 552 times 13. So that's going to change my answer a little bit. Good thing I have the answer key next to me just to double check and make sure you guys get the proper procedure. Okay, I messed up again. Look at that. Boom. All right, that makes more sense. So T is going to be just about 13.536. 13.536. Now, because this is in time, you can think about it as T being equal to 13.5. Well, because you count 1, 2, 3, round it up, or keep it the same, 13.5 minutes. All right? So that is for part B. And then they tell us that this morning, for some reason, Billy walked 1 kilometer up a hill, and it took 22 minutes. And we need to explain why, and this is actually something that happens almost always in these regression line examples, is that you need to explain why it would be inappropriate to use the equation. So everything you did, it's not that it's wrong, but it's, okay, what is good, what is bad about this, all right? And I know some of you might be thinking that you never want to do math again in your lives, but I think it's always important to just have the mentality in general, like, okay, the way you're trying to explain a problem, the way you're trying to model something, whether it's math or not, okay, the way you're thinking about something in your life, what is something about the way you're approaching this issue that maybe is not ideal, that maybe has something that in some certain scenario could maybe not work out properly, okay? I think it's always important to keep this sort of self-criticism going around in your life. And I'm not just talking about your math models, okay? I'm just talking about how you face stuff in general. So sorry for getting boomer on ya, but I think it's important to, be open-minded and criticize always, even yourself. More importantly, yourself. Always with love. So, what would be inappropriate about a linear regression? Okay, that's really what it's asking. What is inappropriate about using a linear regression? So notice how in this case, we, for part B, okay, for part B, we plugged in, this is very important, we plugged in, what did we plug in? We plugged in 13% as gradient. So we plugged in G and got T, which is the same thing, you guys, as if me telling you that you plug in an X and you get a Y, which makes perfect sense, correct? For part C, what you would be doing is plugging in a T, because of 22 minutes, to get a G, which is the same as saying that you plug in a Y to get X. And so that is one thing that you can pretty much always use for these sort of exercises. You can always say that using a Y on X regression line, which is actually the current context, right? Using a Y on X regression line cannot always make a reliable prediction for Y. They are always, almost always, for making predictions. Oops, I said this the other way around. Using a Y on X regression line cannot always make a reliable prediction for X. They're always good for making predictions for Y, okay? And so you're kind of like using it the other way around, not what it's intended, right? So anytime you have a problem where they tell you that you're using a regression line and you're trying to find an X value, you say, nah, usually you want to try to find the Y value. The standard is that you plug in X, you get a Y. And so for part C, you're plugging in Y and getting an X. So you say, nah, this guy on YouTube told me regression lines don't work that way, okay? And I'm not saying that it doesn't always work, but I am saying that you encounter problems, okay? So for regression lines, that is one way you can earn this point, okay? The other way you can earn this point is quite simply saying regression line is for time on gradient, not gradient on time, okay? Which is a very similar idea to what I just said. It's a little less general, but the idea is the same, okay? It was not the intended purpose of the regression line. That's why it's not going to work well, see? The other thing you can say is that this estimate is what they call an extrapolation. And so an extrapolation is something where you look at your correlation. Okay, let's say you have a bunch of points here, right? And you say that the correlation is like this, right? You can try to do an extrapolation to predict values that are over there, right? But the thing is, this regression line is very effective for these values, right? And if you go beyond that, you would be entering the extrapolation sort of area. And so, unless your regression line really considers all the different scenarios and stuff, when you extrapolate, it's likely to be wrong. Now, it depends on the context always, okay? But let's say that you have a very extreme sort of gradient. Let's say that, okay, Billy's dealing with gradients from 0 to 20. Let's say you try to extrapolate for a gradient of 100%, okay? It's literally a vertical wall. Like, time there would be like so much more, you know? It would not be like wise to extrapolate with a very, very high gradient. And so if you suddenly have a very, very high gradient, it's an extrapolation, it's likely to be wrong. And so notice how here you have values from 0 to 20, and here they're talking about 22 minutes. I know it's not that far off. I would personally just use it as extrapolation and it's fine, but you do get a point for saying it's an extrapolation. Okay, so anytime you extrapolate, you can say nah, careful. Okay, so I think the two general sort of arguments you can always use is this first one, okay, and this third one. All right, those usually show up. The other two are like more context wise, and the other two being this last one as well. So the last one that you can say is that you can say that there is no reason to assume this new hill has constant gradients. So now we go back to all the constant stuff we talked about earlier. So our dear old friend Billy, he has been going on gradients that have a he has been going on hills that have a constant gradient. And so maybe this new hill that he's going up, maybe it's not constant. Maybe it's a hill that goes something like this, right? And so that is definitely not constant. And you can say that there's no reason to assume that this new hill has a constant gradient. So the model you should be using is not this one. Okay, that's your argument. And that is 4 different ways to get this 1 point. So again, that was a lot of blah blah, but I think it's important. It's a very easy point, you guys. And even if you get part A wrong or part B wrong, or you don't even know how to start it, or you're running low on time and shit like that, notice how part C is a context problem. Okay, sometimes you have these context problems that give you like it's not that it's 3 points, but like you can do part C without B or A. So be on the lookout for those kind of exercises, especially if you're low on time and you need to claw some points. This one is a context problem, which you can answer, or a constant question, I should say, which is something you can answer right away. All right, that was a lot of blah blah, but I'm sure for some of you it was super helpful. So that is number 1, and I hope it helped. All right, and for number 2, we have the Great Pyramid of Giza is the oldest of the 7 wonders of the ancient world. Damn, that's pretty cool. When it was built 4,500 years ago, talk about being a boomer. The measurements of the pyramid were in Royal Egyptian cubits, REC. And so this is a form of measurement. So you know how there's the whole battle of like meter versus yard, right? Well, the real debate is meter versus yard versus rec. That's what I'm saying. Anyways, point is, this is just a unit of measurement, okay? And so our good old friend Victor really likes pyramids, and he tells me that he reads online that 1 rec is equal to 0.52 meters, rounded to 2 decimal places. So 1 rec is 0.52 meters, around half a meter. By the way, this exercise is using a source from Wikipedia. So you know how your teachers always tell you, don't use Wikipedia? The IB uses Wikipedia. So I'm just saying, everyone's a hypocrite nowadays. Anyways, for part A, we need to write down the upper and lower bounds of 1 REC in meters. And so, ladies and gentlemen, we really need to understand, well, what it means to talk about upper and lower bounds. And so technically, let's say we're talking about the upper and lower bounds of, dude, I don't know, man, like 150, okay? That means that if you estimate it from the lower side, you should reach 150, and if you estimate from the upper side, you should reach 150. And so, for example, you can have, let's say you're rounding to the nearest tenth, right? So the lowest you can go on lower would be 145, right? So 145, because of the 5, you still round it up to 150. And for the upper, I'm sure a lot of you are thinking, okay, for the upper, it would be 154. So rounding down with 154, you're going to reach the 150, right? And here, ladies and gentlemen, is where the interesting debate begins. And I'm going to tell you the stance that the IB has on it. I'm not sure if it's a general math rule, but the idea is the following. So for the upper one, yes, if it's 154, you round it to 150. But what if it's 154.1? Well, I mean, it's still pretty much 4. It's not 5, right? It's not 5, so you're going to keep rounding it to 150. But now I'm going to really push it and say, okay, 4.9. Well, it's not 5, so you don't worry about it, right? What if it's 4.999999999? And here, I'm sure a lot of you will tell me, okay, so that's not 5, so I still round it down. And I say that I agree, but what does your calculator say? Your calculator says it's 155. Damn. And so your calculator is basically saying, dude, it's such a small difference, you might as well just call it 155, okay? And so strictly speaking, in the example I'm giving here, your lower is 145 and your upper is 155, okay? It's just, we first have to agree on that. I know it's a little bit weird because there's a 5, oops. I know it's weird because there's a 5 on your upper. And this is just one of those things I gotta tell you, deal with it, okay? We know that this is technically 154.99999, but for the answer key, for how you should express it, just leave it as 155, okay? So lower and upper is just gonna be +5 and -5 of whatever you're looking for. And so if we are searching for part A, for the upper and lower bounds of 1 REC in meters, well, you know that 1 REC, according to Victor, who looked it up on Wikipedia, a 1 REC is 0.52 meters. And so how can you round from the lower side and also from the upper and still reach 0.52? From the lower side, well, you would do 0.515. And so because of this 5, you would round it up to 2, right? And so for the lower side, for the lower bound, you can already say that it's going to be 0.515. And for the upper bound, we're going to have the same debate that we just had, which is quite simply 0.52499999999. But because the IB is what it is, and because the calculator tells you it is what it is, you're just going to write this as 0.525. All right? And so again, this has to do with that technically this is a 4 with a 9999999 followed next to it. It is what it is. It's even what the mark scheme says, just so you guys believe me, check it out. Upper bound 525, lower bound 515, okay? And so I'm sure some of you looked at this and you were like, why is this not 4999? Technically it is. It's just how you have to answer it. I see upper bound and lower bound appear a lot in tests, so at least now you know how to answer it. Okay, so those are 2 easy points. You just gotta be aware that it's +5 or -5 for upper and lower, okay? Anyways, so yeah, upper bound, we're gonna call it as we saw in the answer key, 0.525. Don't forget your units, meters and meters. All right, so that is for part A. Then for part B, we have that the Great Pyramid of Giza has a square base with side lengths of 440 REC and the height of 280 REC. Victor, our good old friend Victor, assumes that these two measurements are exact and that the Great Pyramid can be modeled as a square-based pyramid with smooth faces. All right. Victor's interested in some weird stuff, but everyone can do their own thing, right? Whatever. And so from here, we need to find the minimum possible volume of the pyramid in cubic meters. And here is a massive buzzword. Your massive buzzword is that they say minimum. And on the other hand, we have the equation for volume of pyramid. So another big buzzword is volume. So the moment you read volume, you should be digging into your formula booklet and seeing where the heck you have the words volume. And so once you've played around with your formula booklet for long enough, you're going to find that volume is, it's in quite a few places. And here, which one are we looking for? Well, we're looking for volume of a square-based pyramid. So volume of a square-based pyramid. Here you have a right pyramid, right? And so the volume of a right pyramid means that it's straight up your pyramid, right? And so from here, A is the area of the base. But you know that the base is what shape? It's a square. And so, okay. So the volume of a right pyramid is 1/3 times big A times H. And big A is the square. And actually, they say it's a square base. See? So that even helps. That even helps more. See? So side lengths 440 and height of 280. So that means you have your pyramid that looks a little bit like this. Let me practice my artistic skills for a second. So you have a square on the bottom, right? And then you have a pyramid that looks something like that, okay? And you know that its height, imagine that's the middle of the square. You know that the height is 280. And you know REC, right? And you know that the side lengths over here is 440. Okay, so you have 440, 440, and technically 440 here and here as well, right? That is what's happening, and all of these are in REC, right? Now, read carefully because the exercise, I don't think I mentioned it earlier, but the exercise is asking you for leave it in cubic meters. So you're forced to turn it from REC to meters, okay? And so, yes, my equation is 1/3 of big A times H, but if I write this in, right? If I write this in, you know that the volume is 1/3. Big A is going to be the bottom part, right? So it's going to be 440 REC twice, because it's a square. Area of a square is base times height. Is that here, actually? Area of a square. It's probably not here. Now I'm just curious if it's here. Yeah, no, they don't have area of a square here. Oh, well, parallelogram, same idea. So base times height, it's going to give you the area of the square. And then we have h for height, right? And so h for height, we said is 280 REC. Now, you want to find this version, but in meters, right? And so to convert the 440 REC to meters, you're going to be taking this same 440, okay, and multiplying it by 0.515 for meters, right? And you're actually going to be doing this twice because it's the area of your square. All of this being multiplied by the height, which is 280, and in terms of meters, 0.515. So what are the main ideas here? The main ideas here are that you need to use the formula of a pyramid. You need to find the area of the big shape at the bottom, which they tell you is a square. And you need to convert the REC into meters, okay? And which of the two are you using? Are you using the lower bound? Are you using the one in the middle? Are you using the upper bound? You're using the one in the lower bound because they specifically ask you to find the minimum possible value. And so for the minimum possible value, you have to use the smallest bound, the lower bound. And so if you plug all of this into your calculator, you're going to end up with a very long line of math. But you go ahead and do that. And my first parenthesis is 440 times 0.515. Again, the same idea, times 0.515. And this is getting multiplied by 280 times the height. The height being 280 times 0.515 to leave it in meters. And as we can see, we get this value here, which is 24,68106. 68106.051. All right. And so from there, we just found the volume of the pyramid in cubic meters. Make sure to not forget your units. You're going to be putting m to the power of 3. All right. If you want to do significant figures, you would count 1, 2, 3. Do you round it up or keep it the same? You round it up. You can leave it as 247. 0, 0, 0, 0, 0, 0, 0, 0 meters cubed. All right, so this is the version with 3 significant figures, if you want. And the thing that's in green is what our calculator spit us out. All right. Anyways, that is for number 2. Not that hard, but you do need to know well what they mean by upper and lower bounds. So once again, buzzwords are the way to go. I hope it helped, and that is for number 2. All right, for this first one, we need to consider the graph of the following function. F of x equals blah, 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 and x cannot equal 0. Why can x not equal 0 in this case, you guys? Because x, as you can see, is also in the denominator. And so, quick question, quick pop quiz. 0 divided by 3 gives you 0. 3 divided by 0 gives you undefined, quite literally. If you ever forget which of these is 0 and which of these is undefined, thankfully you have your trusty rusty graphing calculator. And so 0 divided by 3 gives you 0, and 3 divided by 0 makes your calculator, just tell you error, you divided by 0. You cannot divide by 0. It is undefined. It is a problem in society. Do not divide by 0. And so, point is, x cannot equal 0 because x is in the denominator, see? That is important to understand down the line. For part A, we need to write down the equation of the vertical asymptote of f of x. Now, first things first, what the heck is a vertical asymptote? Actually, even before that, what the heck is an asymptote? An asymptote, the intuition is that asymptote is a number that your function can never be / reach. So say you have a graph maybe that looks like this, okay? And so with ever increasing x values, you can see that this y value sort of like flattens out, right? And so maybe you have a y of 5, okay? And at 5, you have your asymptote. And your function might get very, very close to touching it, but it never actually touches it. Okay, so an asymptote is basically that. It is a value for x or y that your function can never be or reach. And so a vertical asymptote, in this case, just to exemplify, yes, it's y equals 5, it's a y value, but as you can see, this is an example of a horizontal asymptote. Okay? At y equals 5, you have a horizontal asymptote, and, just to make it up, let's say this equation keeps going like this, you could have a vertical asymptote here, which would be at x equals -4, just to make it up, right? And so for an x value, you can get a vertical asymptote. I know that's a little bit weird because we're very used to assuming a little bit that like horizontals for x and verticals for y, but because you're trying to draw the line that it's never going to reach, at y equals 5, you make this horizontal asymptote. At x equals 4, you make this vertical asymptote. If you still don't believe me, let's open up Desmos. And as you can see, if you plug in y equals 4, it's a straight line at y equals 4, right? All of these values have a y of 4, and at x equals -3 or whatever, you have a vertical one. See? All of these have an x of -3, as you can see, and the y changes. All right? So that is a little bit what I'm trying to tell you here. Okay? So how the heck do you find the vertical asymptote? So for the vertical asymptote, it's going to be a value of x. Okay. And what value of x can you never have? 0. So for part A, you literally just say that because x cannot equal 0, the vertical asymptote is exactly at x equals 0. So notice, one thing is the value that your function can't be, and another thing is the value of your asymptote. And so because your function cannot equal 0, the vertical asymptote is at x equals 0. And so if you plug in this thing into your graphing calculator, I'm just going to do it on Desmos because it's quicker, okay? You end up with something that looks very, very weird. But at least you're going to understand a little bit better what an asymptote is, because I'm sure some of you are a little bit lost on that. See? So here you have f of x of this guy. And so as you can see, it looks super wacky, but at x equals 0, this purple line, your function never touches it. Even if you scroll all the way down, it might get very, very close, but it's never actually going to touch. It's never actually going to touch. And so that is the vertical asymptote that we are seeing here, okay? All right, enough blah blah. That is part 1, part A. Part 1, part B, they ask for the famous derivative. And I'm going to point something out right away, you guys. This is worth 3 points. And doing a derivative, in my experience, is really fast. And so when you're doing your test, consider doing this one like right away, okay? Always do what you feel better about first, and really consider that the derivative problems tend to give you like more bang per buck. They tend to give you more points per minute. All right, that's all I'm trying to say. It's a good test taking strategy. Do what you feel good about first and do the quick points first. Okay, no one says you have to do this test in order. Nobody cares. Okay, so just do the derivative. It's pretty fast. Now, the derivative at the IB AISL level, if you write derivative in your formula booklet, you're gonna find one for SL, which is the exponent one, and a shit ton for HL, which we don't care about and we can laugh at them for being HL, okay? So for now, you have the exponent one, see? Now I can tell you to look at this and to find the derivative using the formula, see? Now I think it's very important to understand intuitively what's happening. So guys, really focus on this n. N is on the exponent, and what does n do? N does two things. The first thing it does, I'm going to put it in blue. It's going to multiply in front. And the second thing it does, which I'm going to put in orange, is that you do n minus 1. And so on the one hand, you do minus 1 to the exponent. And on the other hand, you multiply in front. Okay? Now we're about to see a very solid example, but for now, you can think about it as like, I don't know, x squared is going to be 2x and then the 2 minus 1, which is 2x. X to the power of, I don't know, 3 is going to be 3x with 3 minus 1, which is the same as 3x squared. Guys, that's it. That's literally it. Now, they might throw a couple curveballs at you. For example, let's say you have x squared divided by 4. And so the first step before doing the derivative is understanding that this is 1 over 4 times x squared. So if you do the derivative now, you end up with 1 over 4 times 2 times x to the power of 2 minus 1. And so if you combine like terms, you end up with 2 over 4 times x. 2 over 4 is 1/2. Okay? So notice this was before derivative, this was after derivative. Okay? And the last example I'm going to show you, but we're about to see it in action as well, is that imagine you have 1 over, I don't know, x squared. See? So if you try to do the derivative of this, well, you're a little bit complicated because yes, you have an exponent and you can do it like on the bottom, but technically what the more rigorous way is that before the derivative, you're going to put this on top, okay? And whenever you flip, whenever you flip something, put a negative exponent. And so if you want to put this on top, this is before the derivative, you guys. If you want to put it on top, it would end up as 1 times x to the power of negative 2, which is the same as just saying x to the power of negative 2. See? And so now you can do the derivative, and you end up with negative 2 in front times x to the power of negative 2 minus 1, which looks really weird, but follow these 2 steps, okay? Stick to it. Multiply in front, minus 1 to the exponent. Multiply it in front, minus 1 to the exponent. So this ends up being negative 2 times x to the power of negative 3. And so what you can do from here is that this guy, this guy can go on the bottom. So that means you end up with negative 2 divided by x to the power of 3. So the derivative of 1/2 x squared ends up being negative 2 divided by x to the power of 3. All right, so what do we learn here? Well, how to do the derivative of an exponent, right? Multiply in front, do a minus 1 to the exponent, but also, if you ever have an x on the bottom, first put it on top. Then do the derivative. It is much easier to deal with it. So, ladies and gentlemen, we come back over here. We need to do the derivative of this function here. And so before we do anything, let's first observe our function. So if I observe my function, do I have an x on a denominator? Yes, I do, right there. And so first, before doing the derivative, I'm going to put it up top. So I end up with 16 times x to the power of negative 1. Because down here was to the power of 1, right? So if I put it up top, it's going to be x to the power of negative 1. Plus x squared divided by 8. And so if now you do the derivative of an exponent, you end up with 16 times negative 1 times x to the power of negative 1 minus 1 plus 2x divided by 8. And so this first term is going to end up being negative 16 divided by x squared plus, here you cancel out, you divide by 2 on both the top and the bottom, you end up with x divided by 4. So you did divided by 2, divided by 2. You end up with x divided by 4. See? So that is the derivative of f of x. And as you can see, it was super fast. I just needed to maybe explain a little bit the rules of derivative. See? But now that you understand it, now that you understand the flipping thing, now that you have the rule of thumb that, yo, if it's on the bottom, put it up top first. This is very fast, okay? Very fast and generally very easy, okay? Yeah. If you want to follow the mark scheme like to the like in a very detailed manner, they leave the x on top. So they leave 16x x to the power of negative 2 plus x divided by 4. So if you're looking at the mark scheme and you're saying, yo, it's not the same, it is the same, just that we put the x back on the bottom, they didn't. Does it matter for your score? No. Okay? The real part of your score is understanding and doing these 2 things. If you do these 2 things, you're going to get your score. Okay? So just saying up here is the mark scheme. And for us, it's more intuitive to leave it like this one on the bottom. See? All right. Anyways, then they tell us 2. write down the interval in which f of x is increasing. Now there are a couple ways to do this. See? The first way to do this is that you put it into your graphing calculator, okay? And you see where your equation is increasing, okay? Your equation increases if as x travels to the right, you have a y that goes up, okay? And as you can see from Desmos, it's very easy to see that it only goes up from here, see? And so one thing you can do is find this vertex, find this minimum, and say, okay, from here to the right, it grows, see? And so technically what we're going to reach, now I'm going to show you how, okay? But what you're going to reach is that it is increasing only from 4 to infinity, see? So there's a couple different ways to do that. You can say, okay, from 4 to infinity. You can also say from 4 to infinity, or my favorite one, just x being greater than 4. See? So whenever x is greater than 4, we're talking about the right side of this function, clearly where it's growing, the only part where it's increasing or growing. See? Now, how do you reach that without Desmos? Because Desmos is very easy. Well, you can actually take your graphing calculator and graph it. Heck, that's why it's called a graphing calculator. So you do take 16 divided by x plus this other fraction. By the way, I'm doing the fraction by using alpha y equals. Okay, alpha y equals, you hit the first one, you open up the fraction. Here you can put x squared plus 8. See? So if you go ahead and graph this, you're probably gonna not see it well because your window is probably all messed up, which is pretty normal. See? And so what you can do is go to window and change it a bit. See? Now before changing it a bit, I suggest you go to zoom and then zoom fit. Okay? Zoom fit usually makes your window more friendly, although not always. So from here, you can clearly see that there's a growth, right? But you need to see from where, okay? And technically, what we're seeing right now in your calculator is a very, very zoomed out sort of graph, see? So to make it a little bit more friendly, you play around with the window. What I suggest is that you put like the same values for everything. So you can put like, I don't know, -20, max 20, minimum -20, maximum 20. See? So you go ahead and graph, and now it's a little bit more friendly. And so from here, again, this was just intuition to make your numbers smaller, but eventually you find a nice graph, and all you really need is to understand how it looks like. So now that you understand how it looks like, you say, okay, it's only growing after this minimum. So how do you calculate minimum? Well, go to second, trace, hit the calc button, and here you have a minimum. So you can press minimum, and here it says, it asks for left bound, right bound, see? All that's really doing is that you are defining like where you want your calculator to scan, okay? So right now we have a graph that looks a little bit like this. You have a graph that goes like this, and then a graph that goes like this, okay? And so if you pick the left bound here, which is like around there, okay? And then you pick the right bound, I don't know, here, which is there. And then it asks for guess. The guess is really just for you to pick the minimum that you want, see? And so what your calculator does is that it's going to scan this and find all the minimums in this area. It's going to find just one, see? If there were two, the guess function would help you pick which one you want, okay? But this is what it's doing. It's scanning and finding one for you, and there it is. And so the minimum is at 3.999, comma 6. Now 3.99999 is the same as 4. So you can say that technically the minimum was at 4.6, and so whenever x is greater than 4, it's going to be growing, okay? And this is merely like a visual way to solve it, see? The more mathy way to solve it, if you want to, and a way that actually relates that that part C needs something from part B is using the derivative, okay? And so technically, guys, always remember to optimize or to find max/minimums, derivative equals 0. See? Now let's explain a little bit why. Even in this same function that I just drew, you have a lot of different slopes here, right? And so the derivative, what it does is that it now helps you find slope. The moment you find the derivative of a function, all it will give you now is slope, okay? And so if you say, I don't know, the derivative, I mean, you have the derivative and you equal the whole thing to like 2, okay? You're going to be asking your function, where's my derivative 2? And so what you're going to get is that the slope of 2 is around here, right? Because it's positive, it's growing. The slope of 2 is around there, and you're going to get the x value where the slope is 2. And so the maximum or minimum has a slope of what? It has a slope of 0. Kapow, look at that. So a slope of 0 gives you the max or min, okay? And as you can see in any graph, imagine a graph that looks like this, okay? Notice all the maximums and minimums, okay? Notice all of them. And notice how the values next to them behave. For example, here, entering to the left, you have negative, 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 negative. It's going down. You have the vertex, or you have the minimum, and boom, it starts growing. And until the next vertex, boom, it starts decreasing. And until the next vertex, boom, it starts growing. And until the next vertex, boom, it starts decreasing. And until the next vertex, boom, it starts growing. And so on and so forth. Why is it important to know this? Because if you were trying to find where it is increasing, all you have to do is find one of these maximums or minimums and say, okay, from here to the right, it's going to be growing. Or maybe you have a graph that's the other way around, right? That looks like this. You're going to say, oh, okay, so here it's increasing. And from there forward, it's just going to decrease, okay? Point is, maximums or minimums can help you identify where your thing is increasing. And so what you can do is that you can take this derivative and equal it to 0 and get an x value from there. Now that is a little bit harder in this case, but in other cases, it's actually faster, see? Or if you don't like the graphing calculator and you find that playing around with the window is super hard or it's very time consuming, you might find that this is quicker. So let me show you how you would do it. You're going to take your derivative, you're going to equal it to 0, see? So basically on this step, you're saying when the slope is 0, when the slope is 0, what is x? Okay, that is the main idea. When the slope is 0, what is x? That is what you're doing here. And so when the slope is 0, what is x? Here's my function for derivative, okay? So from here, you need to solve for x, see? Now solving from x here is pretty annoying, okay? There's not always like a straightforward sort of way to do it. The quickest way I see, although it's pretty big brain, but the quickest way I see is that right now you're very annoyed by having an x squared on the bottom. So what we can do is multiply everything by x squared. So you multiply everything by x squared, you end up with 0 equals negative 16, because you get rid of this with this, plus x cubed divided by 4. You can do plus 16 to both sides. You end up with 16 equals x cubed divided by 4. You want to get rid of this 4, right? So you can do times 4 to both sides. This goes away with this. You end up with 64 equals x cubed. Now, to get x cubed, you have to do square root. To get rid of any exponent, you do square root. So you do square root, but not the normal one, the square root with a little 3 on top. See? And so you do a square root with a little 3 on top. This goes away with this. You end up with x equals square root 64 with a little 3 here. See? And so how do you do that in your calculator? You gotta go to the button math. You gotta scroll down, and here you have a 3 with your square root. See? And you plug in 64, and there it is. You get 4. Now let's understand for a moment what this actually did. what this did is that, well, first of all, you found the same 4 as before, right? You found this for here, for x, okay? You found this for here for x, and that can basically tell you, okay, there's the minimum, so from here to the right, it's going to be increasing, okay? Now, you also have to find out if it's a minimum or maximum, so graphing is probably the ideal, okay? But anyways, if you want to be hardcore and do it with derivatives, this is one way to do it. I'm just pointing it out, okay? I suggest graphing it instead, but I'm sure some of you want to see this alternative. Now let's understand what the square root even did though. See? Normally, let's say you have square root of 4. You immediately tell me that that's 2. Or square root of 9. You immediately tell me that that is 3. This is because you are finding the number that multiplied by itself twice gives you what's inside. The number multiplied by itself twice gives you what's inside. So 2 times 2 gives you 4. 3 times 3 gives you 9. Now, why is it multiplied by itself twice? Because your square root has a little 2 over here that's hidden, that you're not writing but is always there. Okay, this is no different than if you have, I don't know, 3 squared plus 2x plus 5, okay? You're not writing that x is to the power of 1 because it's implied, because it's obvious, okay? For square roots, it's the same. There's always a 2 hidden, and that tells you, okay, which number multiplied by itself twice gives you 4? Which number multiplied itself twice gives you what's inside? 9. And so the moment you face this, which number multiplied by itself 3 times gives you 64? 4 times 4 times 4 gives you 64. Because you end up with 4 times 4 is 16. 16 times 4 gives you 64. And so 3 square root 64 equals 4. All right, you guys. That was a pretty long explanation, especially for part C. But I'm the kind of guy that likes to show you all the ways to do it. You pick the one that floats your boat. You pick the one that is the most friendly for you. And to my intuition, to my knowledge, graphing it, if you're familiar with the window and how to like get it quick or whatever, graphing it is probably the way to go. Okay? That is my suggestion. But at the end of the day, do whatever makes you feel good. Do whatever is more comfortable for you. I'm just showing you the options. You figure out what's best for you. I hope it helped. That is for number 3. Alright, number 4 we have on the following Voronoi diagram. Hot damn, Voronoi diagram. The coordinates of 3 farmhouses are A, which is this guy here, ba ba ba, B, which is this guy here, da da da, and C, which is this guy here, la la la. Where distances are measured in kilometers. Okay, so all my answers will probably have to be in kilometers. Each farmhouse owns the land that is closest to it. Okay, that makes sense. So, for example, farmhouse A owns this whole piece of land. B owns this whole piece of land. C owns this whole piece of land. That's fair. Their boundaries are defined by dotted lines on diagram 1. And to provide water to the farms, it is decided to construct a well at the point where the boundaries meet on diagram 1. And so where the boundaries meet is, of course, where all these dotted lines meet. So it's got to be right there, of course. And we need to write down the coordinates of this point. Now, believe it or not, especially when the IB usually says, usually they say, diagram not drawn to scale. Ladies and gentlemen, do you see that anywhere here? Because I don't. I don't think it's anywhere. See? And so the diagram is drawn to scale, so that means you can count. Okay, for this point that I'm putting in blue, clearly it's at x equals 4, right? And clearly it is also going to be at a y of 8. And so part A is actually incredibly easy. You can just say that A is 4, 8. All right? And so that is for part A. For part B, we need to find the equation of the, oh my lord, the perpendicular bisector of AC. And so before we move any forward, I am obligated to talk a little bit about what a Voronoi diagram is, what it means, how it works, and all that stuff. Okay? So the Voronoi diagram, as you can see, helps you split up your points into equal distances from each other. It's not so much equal areas, it's about equal distances from each other. For example, from C to B, okay, notice how they have the same x value, okay? They have the same x value, all right? They both have an 8. And notice how far away they are in terms of y. Okay, so they both share the same x value, but how far away are they in terms of y? Well, up here, you have 13, right? Down here, you have 3. So that means in the middle, you have 10, and that means that this distance here is exactly 5, and this distance here is exactly 5. And so the cool thing about Voronoi diagrams is that these different points are, or better said, the dotted lines, okay, these dotted lines help you know where the equal distances from each other are, okay? For example, from A to B, you have from 0 to 8, right? So that means from here to here is 4, and from here to here is 4. And so yes, from B to C was 5 and 5, from A to B it was 4 and 4, and from A to C, I'm sure it's a different number, okay? But that's the idea of Voronoi diagrams. It creates these dotted lines so that all these distances from A to B or from B to C are equal to each other. 5 and 5, 4 and 4, etc. Why would this be useful in real life? Well, here's an example of a farmhouse and, a wind turbine and stuff like that. But also maybe for like city architecture, right? So imagine you're trying to like, I don't know, put 3 different malls, okay, at a distance that are equal from each other so that you can sell more, okay? Or you want to put 3 hospitals that are at a equal distance from each other so you can help more people, or schools, or police stations, or whatever, supermarkets, anything, okay? That is why Voronoi diagrams can be useful in real life. Yes, some of math is actually useful in real life. So, that is a Voronoi diagram, right? And here, as you can see, it is filled. It is filled with what they call perpendicular bisectors. Okay? And so this line in red is simply the line that goes from C to B, but the perpendicular bisector of C to B is this guy here. This that I'm putting in green is the perpendicular bisector of CB. Why is it the perpendicular bisector? Well, perpendicular because the slope is perpendicular. Okay, perpendicular because the slope is perpendicular to CB. And bisector because, it's exactly there. It's exactly in that dotted line that I spoke about earlier. It's exactly in this dotted line, right? That it splits up with 5 and 5. So bisector, bi, same as bisexual, 2. So you're cutting it into 2. You're bisecting into 2. That is why it's 5 and 5. Point is, just so that we really understand Voronoi diagrams, and with this I'll start part B. I just think it's important to understand context. You have 3 perpendicular bisectors right now. You have the perpendicular bisector of C to B. So I'm going to put the normal lines in red. Okay, so the normal lines are C to B, B to A, and A to C. So these are your 3 like normal lines, whatever, okay? For example, here is 5 and 5, here is 4 and 4, and this other one I didn't calculate it, see? But it's going to be x and x, same distance, right? So these in red are the normal lines, and the perpendicular bisectors I'm going to put in brown are this one here. So this is a perpendicular bisector because it cuts it into x and x. Here is another perpendicular bisector because it cuts it into 5 and 5. Here is another perpendicular bisector because it cuts it into 4 and 4. Okay, that is the idea of perpendicular bisectors. That is what it's asking for. And so for part B, for finding the equation of the perpendicular bisector of AC, we first have to focus on this red line that I'm leaving on screen now. okay, we gotta focus on this red line, find the slope of this, and then I discover this other thing, okay? Yeah. So what is the slope of the red line? Well, you have an equation for slope. In fact, in your formula booklet is this thing called, whoops, it's this thing called gradient. So gradient, let's just remember that gradient equals slope, okay? And what do you need for this gradient formula? You need y2, y1, x2, x1. What the heck is x2, y1 or y2, y1? It is just two pairs of points. So x1, y1 makes reference to a set of points. The 1 gotta go with the 1. x2, y2 is a point of two other points. So let me go over here and say that m of red, right? So m of red is y2 minus y1 divided by x2 minus x1. And so in this case, what is y1, what is y2, what is x1, what is x2? I'm going to call this 0 x1 and this 3 y1. So point A is my first point. This 8 is going to be x2 and this 13 is going to be y2. So my slope over here is 13 minus 3 divided by 8 minus 0. Okay? So right now I'm going to have 10 divided by 8 is my slope of the red line, which is 5 over 4. So the slope of the red line is 5 over 4, right? Now the perpendicular bisector, as we recall, is this line that cuts like this, right? And so because they're perpendicular, well, the big question we have to ask ourselves is what is the perpendicular slope? Slope to 5 over 4, okay? Now, there's two types of slope you guys can encounter. You have perpendicular slope and you have parallel slopes, okay? For a perpendicular slope, the equation, okay, is that your first slope times your second slope equals -1. And for parallel slopes, it's simply that your first one equals your second one. Remember that parallel slopes look like this, and the only way for them to never touch is if they always grow at the same rate. So if m1 equals m2, they will never touch. That is for parallel slopes. For perpendicular slopes, it's m1 times m2 equals -1, which I know looks very weird, but we can make this a little bit more friendly. For example, if I go ahead and say, I don't know, divide by m2 to both sides, this goes away with this, so m1 equals, technically it's -1 times 1 over m2. So for perpendicular slopes, two things have to happen. First, for perpendicular slopes, you will, why is this not working? Okay, you will first multiply by -1, which is what this guy here is doing. And secondly, first and second, you will flip it. So notice how this m2 used to be above, now it's on the bottom. So that's what I mean by flip it. All right, so let's apply that to this 5 over 4. So this 5 over 4, I can first multiply by -1, so I can end up with -5 over 4. And now I'm going to flip it, -4 over 5 is the slope of my perpendicular bisector. If you want to be more hardcore about it, you would say that m1 times m2 equals -1. So that means that 5 over 4 by m1 times m2 equals -1. And so now you can get m2 alone, so you can do times 4 times 4, so bada bim bada boom. 5m2 equals -4, divide by 5, divide by 5, m2 equals -4 over 5. All right? Two ways to do the same thing. You either remember the multiply by -1 and flip, or you go hardcore from the formula. See? Whatever works for you, I don't know, you figure it out, your life is yours. So for the perpendicular bisector, we found that its slope, so I'm going to put it in green, right? So the slope of this guy is going to be -4 over 5, right? Now, I found the slope, but now I still need to find the rest of the equation, right? The slope was very important for it, but for finding the equation, I need to create it. And so, well, this is what we would call a straight line. I mean, it literally looks like a straight line, right? It's a straight line. And so in your formula booklet, here you have equations of a straight line. See? Now notice you have 3. And this is not to be mean, well, a little bit, but you have 3 and you gotta know which one to use, okay? A lot of times you're gonna notice that they tell you like, oh, leave your answer in this form, or leave your answer in this form, but they almost never say leave your answer in this last form, and that's for a reason. Guys, rule of thumb for creating equations of a straight line, use the last one. The last one is what we call point slope form. It might point slope form, it might sound a little bit more familiar, okay? So this last one is point slope form. And notice, what does point slope form ask for? Well, the y and x is something you're not going to touch because it's, part of the equation. It's naturally, it's going to stay there. But you need y1, you need m, and you need x1. So what you really need is a point of x1, y1 on your line, and you need the slope, which is m. So ladies and gentlemen, right now we found our m by identifying that it's perpendicular to the red one. Right, here's my slope in green. And now I need to find a point, right? This red one, this green one, and the red one actually seem to cut through this point here. So that's interesting. Once again, the IB loves to do this. Part B needed something from part A. So the coordinates of this point 4, 8 also runs through the green one. So the point you can use is 4, 8. So if you plug all of this into y minus y1 equals m times x minus x1, you're going to end up with, give me a second, you are going to end up with y minus 8 equals your slope, which is negative 4 over 5, times x minus 4. And technically, just so that you guys know, from here, you're done. Okay? And back in my day, you had to find like this form here to get full credit. For us, and looking at the answer key, you can just leave it like that. Literally. You can just leave it like that. All right? For me, it makes more sense in my brain to leave it in like its final form, which would mean, and this is just to be a little bit more rigorous, I multiply here, so y minus 8 equals negative 4 over 5x plus 16 over 5. So here you can do plus 8 plus 8. Y is going to equal negative 4 over 5x plus, I guess I can leave it in decimal or whatever. Actually, I think I'm going to choose to leave it in fraction. So for fraction, it would be 6 over 5 plus 8. I want to be able to add the two fractions together, so I need to amplify this one by 5 so that they have the same denominator. So y equals negative 4 over 5x plus 16 plus 40 divided by 5. So y is going to equal, this is for part B, y is going to equal negative 4 over 5x plus 56 divided by 5. All right? So a couple extra steps, but I would just rather have it like in its final form or whatever, okay? Anyways, that is for part B. Then they tell us that an additional farmhouse at D of 6, 5 is built on the land. The Voronoi diagram has been redrawn to show the new boundaries. Why does the Voronoi diagram need to be redrawn when you add a farmhouse? Because the Voronoi diagram, its whole point is that the dotted lines show you equal distances from each of your key points. And so if there's a new key point going around, you need to make a new dotted line. So now, from here to here, these are the same. From here to here, these are the same. From here to here, these are the same. All right? That is why that happens. All right? And so they tell us that a wind turbine is to be built at one of the vertices, right? Vertices, think about it as like anywhere you have sort of like an edge, right? So an edge like this, an edge like that, an edge like this. All of these are vertices, see? So technically your three vertices that we're considering are this point here, this point here. All right, let me just leave it a little more clear. So that point, that other point, and this, oops, and this last point here. So all of these three ones are vertices, and a wind turbine is to be built at one of these, right? Now they want, for part C, that the wind turbine should be as far from the nearest farmhouse as possible. So for C part I, we need to calculate appropriate distances, find the location of the wind turbine. And so clearly, well, you just gotta pick one of these vertices and just sort of compare it to any of the farmhouses. And do this with the vertices a couple times, right? And so whichever one is like the farthest one away is the one you're gonna pick, okay? And so just just intuitively, right? I think it's pretty evident that this one down here you're not gonna consider. It feels a little bit too close to A, it feels a little bit too close to B. I don't think it's this one, right? But I do have my doubts which one is the winner between this distance and this distance. Here is a question, which of these two wins, right? And so, okay, we're talking about distances, right? So how can I find the appropriate distance? Huh, distance. Far from, distance, far from. Formula booklet, buzzword, distance between 2 points. You have a version where it's x, y, z. Distance between, that's HL, we don't care about it, we just laugh at them. Distance between 2 points, here it is, bada bim, bada boom. You have the distance formula, ladies and gentlemen, to find the distance, of course. And so, let me erase this to make a little bit of space. But notice how my procedure from just now was thinking about, okay, what are the buzzwords that are throwing at me? What do I need to find? And through there, you unlock which formula to use, okay? The best way to identify the correct procedure is thinking in buzzwords. And here you have the buzzwords of distance, and so you attack it from there. So, distance is, following the formula booklet, we have square root of x1 minus x2 squared. Oops, that's a weird squared. Plus y1 minus y2 squared, okay? So if we use this formula, we should be getting the right answers all along. And so we're gonna be comparing these two scenarios, right? We're gonna compare this one to this one and this one to this one, okay? So for the line that's in blue, okay, we're gonna have blue and then, I don't know, green, okay? So for the case that's in blue, we have that this is x1, this is y1, this is x2, this is y2, all right? So x1 was 9 over 11, so d equals square root of 9 over 11 minus x2, which is 8. So minus 8 squared plus y1 minus y2. So y1 is 116 over 11. 116 over 11 minus y2, which we said was 13. 13 squared. So distance of the blue line is going to be that whole thing, right? So we pull up our calculator and we can say, we can just plug it all in, right? So square roots of, I'm going to put a fraction by using alpha y equals. So 9 divided by 11 minus 8, oops, minus 8 squared plus my other fraction, right? Again, another my other parentheses. Sorry, it's been a long day. Ain't it a long day for all of us nowadays? Minus 13, close, squared. Bada bim, bada boom, there we go. So the distance of the blue line is going to be 7.589. 7.589. I'm just going to leave it like that. 7.589. If you want to consider significant values, you would count 1, 2, 3, round it up or down, round it up. So I'm going to leave it as a significant value just because, I'm like that. 7.59, and our units are kilometers. So for the blue line, this is our distance, right? And so now we gotta see if the green one is farther away. See? Now notice, I'm gonna do this not to be mean, but just so that we keep it in mind. For all of these formulas, okay, the x1 and x2, y1, y2, it's all relative, okay? You pick the first point and the second point. As long as you are consistent and shower, it'll be okay. All right? Point is, from here, for the green one, I'm going to say that this is now x1, y1, and this is x2, y2. And you might be telling me, oh, but sir, uh, I thought 8 and 13 was my second point. And I'm saying, well, you know what? I want to do it differently this time, because why not? Okay, so my first point is going to be C. My second point is going to be my vertice, okay? You can do it this way as long as you're consistent, okay? And it's very important that we understand this, because all along the formula booklet, and this is something I actually don't speak about enough, all along the formula booklet, there's a bunch of different like x1, x2, y1, y2, and or even here, sine rule is an excellent example. See? So for sine rule, you have 3 equal signs, right? So technically, you can do any sort of pair that you want. Okay, you can do this one with this one, and this one with this one, right? Or even for CAB, guys, you define what C is, you define what A is, and you define what B is, okay? As long as you're consistent, for example, in the cosine rule that the side you pick is the same as the angle you pick, because you have cosine C, you'll be fine, okay? Same in the other version, as long as you're trying to find the angle of the side that you're subtracting, you'll be fine, because here you have a minus C. Notice how A and B, you can flip them from place, but C is the one that has to be negative. So as long as you're consistent in that sense, you're fine. As long as you're consistent in that sense here, you're also going to be fine, okay? Point is, the formula technically is kind of like you have a first point and a second point. This isn't x2, y2 for the rest of time, okay? It just depends on how you use it, how you apply it, stuff like that, all right? Because then some people start thinking, oh, dude, like this one has to be x2, y2 forever, and then they get confused because maybe this one you called it x3 earlier. All right, it's all about context. You use the formula however you want. See? That is my point. I hope it made sense. Back to reality. We're going to be applying the distance formula with these 2 points. See? So we have the points. I'm just going to write it down here this time. So we have the point C, which is 8, 13. And then we have the vertice, that is 11, 8. See? 11, 8. And this time around, I'm calling this x1, this y1, and this x2, this y2. So if I apply the distance formula, which I have it in orange, right? The distance formula is going to be square root of 8 minus x2, which is 11 squared, plus 13 minus 8 squared, all right? And so this distance is just going to be negative 3 squared plus 5 squared, okay? And well, really, you can just plug it into your calculator, but now I'm just doing it. So 9 plus 25. So you end up with d equals square root of 34. All right. And so square root 34, if you want to be able to compare your numbers, is 5.830. 5.830. Okay. Right. And so you can count 1, 2, 3. Do you round it up or down? Do you round it up or keep it the same? You keep it the same. So the D line, the green line is 5.83 kilometers, okay? And so right now we're comparing the green to the blue. So the blue is going to be, the green is going to be, damn, I'm getting all my words confused. Happens to anyone. The green line is 5.83 kilometers. So guys, back to the context of the problem. Why were we even doing this? We were talking about that the wind turbine that they want to build that has to be on one of the vertices has to be as far as possible from the nearest farmhouse. Okay? And so as long as you compare at least two different lines, it's enough of an argument or for which one you should pick. See? Just visually, you can tell that down here, you're not going to have the wind turbine. Like, there's no way, okay? But you are between these two wind turbines, right? And you might have the doubt of comparing it to D. But for me, visually, you're comparing just the blue and the green, all right? Point is, and I'm about to show you in the formula book, I mean, the answer key anyways, once you compare at least two distances, but because they do ask you calculating appropriate distances, find the location of the wind turbine, so like find the best scenario. Well, here I found two distances, so that is good enough. And we're basically going to say that this one is the one that's farthest away. So for part CI, the location of the turbine has to be this guy here. Okay, so location of turbine is 911, comma, 11611. See? Why? Because it's the farthest one away. And how far away is it? Well, how far away is it? The line that's in blue, 7.59 kilometers. All right? Just so you guys really believe me that this process of finding just the blue and just the green is good enough, look at the mark scheme. See? Look at the mark scheme and it says for part C, attempt to find one distance from a farm to any vertex, which is what we did, and find the correct distance from at least two distinct vertices. And so the ones that we found were this 7.589, which you left it at 7.59, and this square root 34. And so there are my at least two. You could have done a third, but you didn't need to, okay? But with at least two, it's fine. That's what we did. That was our approach. The mark scheme liked it. That is, for number 4, that is the Voronoi diagram. So it tends to show up at least once per test. If it doesn't show up on paper 1, it will show up on paper 2. So careful about that. I hope it helped, and I'll see you around. All right, you guys, for number 5, okay, we have that Ron sails his boat from point R for a distance of 150 kilometers, which is right here, on a bearing of 120, and which is this 120 over there. When they say bearing, you guys, it's always you start from north, and let's say a bearing of 30 would be you count until you reach 30, okay? A bearing of, I don't know, 200, okay? You would first face north and then count until you reach 200, which would be around there, okay? So around here would be a bearing of 200, all right? So that is what bearing does. That is why it's labeled as it is. For bearing, you always start facing north, and whatever degree you get is the bearing you're going to be doing, okay? So anyways, that's why it starts off with a bearing of 120, and they arrive at point S, okay? And then he sails on a bearing of 38 to reach point T. Ronce's journey is shown in the diagram. And we need to find part A, RST. And so clearly RST is this whole thing over here. And so it's going to be 38 plus something, right? And the interesting thing about these bearing exercises is that technically you were filled with what we call parallel lines. As you can see, all of these dotted lines are facing north, right? All of these are north. That means all of these are vertical. That means all of these are parallel, okay? And you can make a bunch of different rules and a bunch of different properties come out because they are parallel. I need you guys to understand that what I'm about to do, I can do it because these lines are parallel. See? I know I said parallel like 10 times in the last 12 seconds, but it's really important you guys notice these are parallel lines, and so there's a property that comes out of that. If you have two parallel lines that cut like this, so you have one like this, and you draw a line that, whatever, intersects both, okay? a couple properties come out of this. See? So on the one hand, this angle that's in green, okay, is the same as this angle that's in green. And this angle that's in green is the same as this angle that's in green. So all of the greens are equal to each other, okay? As you can see, this right here is just a snapshot of this right here. It's like the same picture. There are no differences between those two things, okay? And so with that in mind, technically this angle here is the same as this angle here, all right? And this angle here is the same as this angle here. So all the blues are equal to each other, all the greens are equal to each other. And one more observation we can do, notice how in this straight line, how many degrees does a straight line have? A straight line has 180 degrees. And so green plus blue, so I'm just going to be very detailed. So in this case, if you do green, okay, plus blue, you're going to have 180 degrees. All right. So a straight line has 180 degrees. And so if you cut it down through the middle, you know that, or you cut it through some way, right? You know that this one plus the other one has to be 180. Okay, that's what I'm trying to portray to you guys. All right. So why is this useful? Well, because you have a bunch of parallel lines, extend them. So if you go ahead and extend these lines, so I'm going to extend one over here and extend one over there. Now suddenly you have something very similar to what's going on over here, right? Only that it's sort of like flipped, okay? But the same idea applies. So let's go piece by piece. If this is 120, then you guys, how much is this? Ah, that's going to be 120. I mean, sorry, that's going to be 180 because it's the whole angle, right? Minus 120 gives you 60. Ah, okay, so this thing in purple is going to be 60 degrees. And so if this is 60, then technically, if this is 60, then technically this one over here is 60. Now I really need you guys to see this because this step is a little bit weird, okay? But technically you are replicating this parallel lines property, okay? Just to make it more visually appealing, I'm going to plug in some colors here, okay? And so technically, if I draw out these lines a little bit more, just to make it even more friendly, notice how, remember how I said green with green are equal to each other? Okay, so this is equal to this is equal to this, whoops. And for the blue, you would have that this is equal to this, and that this is equal to this whole thing, okay? So that is the property that I just used. Green equals green, blue equals blue. And so for RST, you're just gonna have to do 60 plus 38 gives you 98. So angle RST is 98. The way you get it is by what they call, if you want to Google it later, I'm pretty sure it's supplementary angles. If not, just put parallel lines properties and you're probably going to run into it, okay? Intuitively, just draw this image. It's probably the best way to describe it, okay? Anyways, that is for part A. Then they tell us that point T, okay, is directly east of point R. So point T is directly east of point R. So boom. Now, why might it be useful that they say directly east? It might be important that they say directly east because, now you know that this is a straight line. Okay, but this north is also a straight line. Boom! So you got one straight line going up, you got one straight line going to the side. That means that, big thing to do here. Here you have 90 degrees. Here you have 90 degrees. And so if this original is 120 and this part here is 90, that means this last sliver over there is going to be 30 because 120 minus 90 gives you 30. All right, so this is 30. This whole thing is going to be 98. All right, so this whole thing is going to be 98. And that also means that this last angle, right? Notice how I'm filling in information before I even read part B. I'm just filling in information from what they gave me. Fill in information, then try to solve it. Okay, so fill in all information. You can say that this last angle is going to be 180 because it's the sum of angles in a triangle. So 180 minus 98 minus 30 gives you that 52. So here you have 52. All right. And we need to calculate the distance that run sails to return directly from point T to point R. So it's the distance of X of this whole red line. Now, I've been scribbling this diagram a lot, so let me just make a small summary down here. So if I make a small summary down here, what you know is that you have the points R, S, and T, and you have an angle here that is 98. You have an angle here that is 30, I think, yes. And you have an angle here that is 52. Last but not least, you need to find X from R to T, from T to R, and you know that this is 150. All right, you guys, there's a couple tools we can use here. And depending on your approach, some of them might be more friendly, others might not. But what I highly suggest is that you consider this a trigonometry problem, okay? And guys, for any trigonometry problem, I want your approach to be the same. For any trigonometry problem, you will first try the sine rule. If the sine rule doesn't work, you're going to go to the cosine rule. And if the cosine rule doesn't work, you probably just need to get like creative and consider SOHCAHTOA, okay? When I say SOHCAHTOA, I mean sine, cosine, tangent, okay? And when I say SO, it's, just to clarify in case anyone's confused, SO is opposite over hypotenuse, ka is adjacent over hypotenuse, and TOA is opposite over adjacent, okay? I'm not going to go into this because in this video, we're not going to use SOHCAHTOA, but please remember that SOHCAHTOA is only for right-angled triangles. If it's not right-angled, you can't use SOHCAHTOA. Only use SOHCAHTOA if you have a right-angled triangle. Very, very important. Please don't forget it. All right, guys. So anyways, you're facing a trigonometry problem. The first step, you will always try the sine rule. Now, some of you are probably thinking, damn, I never really learned the sine rule. So you're about to learn it with me. If you go to the formula booklet, remember the formula booklet is one of the tools you will be having the day of the test. Look up sine rule. And as you can see, you have little a, big A, until B and C, right? Let me exemplify a little bit what this means. And so there's a difference between the big letters and the small letters. The big letters, notice how they are inside sine, okay? And we're very used to seeing stuff like sine theta, right? And so theta is always used for an angle. What am I trying to say here? Whenever you have sine something or cosine something or tangent something, that something is always, always, always going to be, no matter what, an angle, okay? So these big letters are angles. And so this big letter A has associated to, side little a. This big angle B has the side associated little b. And this side big C has the side, this angle big C has the side associated little c, okay? So point is, it works in pairs. It works in pairs of angle slash side. So as long as you have at least one pair, or like 3 of the 4 things you need, right, you can use one of these equations. Let me be a little bit more clear on that. So the sine rule says that you have little a over big A equals a little b over big B with sine, right? And little c over big sine C. So technically, because you have 2 equal signs here, you can look at it as only little a over sine A equals little b over sine B, all right? And technically from here, if you want to understand it very intuitively, all this is really saying is that you have your side, like side 1, over sine angle 1 equals your side number 2 divided by sine angle 2. And you pick which is quote unquote angle 1 or which is quote unquote angle 2, okay? So in this case, what is the only side I have? The only side I have is 150. And what angle is associated to 150? 52. And what are you trying to find? X. And X is associated to which angle? 98. Ah, so that means you can plug in. So 150 over sine of its angle, which is 52, equals X of its angle sine 98. So if you want to get X alone from here, all you need to do is multiply by sine 98, makes this go away with this, and you end up with X equals sine 98 times 150 divided by sine 52. And you put all of that into your calculator, and you first make sure that your mode is in degrees. Okay, make sure your mode is in degrees. And from here, you just gotta do sine 98 times this whole thing, right? I'm gonna open up a fraction by pressing alpha y equals, pressing the first option, you can put 150 divided by sine 52, and this is your value for x, and x is gonna be 188.50, all right? And that is, oh, and hold up, we are talking about kilometers. So don't forget units, 188.50 kilometers. If you want to round it up with significant figures, you would count 1, 2, 3. Do you round it up or does it stay the same? You round it up. So x in significant figures is 189 kilometers. All right? You guys, that is for part B, and that is actually for number 5. I don't find it super hard, but I do think it's awfully specific to know the parallel lines thing. Okay? And so just remember, anytime you have a bearings problem, anytime they do a bearing, you have a straight line up north. See? And all of these straight lines up north are all the same line, and so you can probably do some trick with parallel lines. All right? So that's a small but specific thing you gotta know. I think it's pretty hard to spot it, but like much in life, you see it once and you see it always. Okay? So get familiar with it. You'll never like miss it again. See? All right, guys. I hope it helped. And remember, for trigonometry, follow this process. Okay? Maybe you see a shortcut of using SOHCAHTOA immediately, and if you do your thing. But I just want to show you a process that always works. Okay? It might take a little bit longer, but it's a process that always works, and that is what I like to teach the most. Procedure. Okay? Facing a trigonometry problem, first try sine rule. If not, go to cosine rule. If not, you probably gotta get creative, or you're missing information, or you can just use SOHCAHTOA or stuff like that. See? Alright, guys. Now it's concluded. I hope it helped. I'll see you around. That is for number 5. All right, guys, number 6 is not that hard, but you do have to know what it's asking for. So you have the following function, h of x equals blah, 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 nobody cares. See? You have that x has to be greater than 1. Let's understand why. So here, where is x? X is right there. It's in the denominator, and it's also in a square root. So square root of x minus 1. Now, you guys, for a square root, let's say you have square root of, I don't know, 9. It's going to be 3. Square root of 8. It's going to be some number, right? A little less than 3. I don't know, 7. You can keep going. You're going to get the idea. See? Point is, notice what happens when I enter the realms of negatives. It's very interesting what happens. So square root of 3, which number multiplied by itself gives 3? That number. So this times this is going to give you 3. Okay, that's what the square root does. Nice. Square root 2 is 1.14, I think. 1.414. Sure. So this times itself should give you 2. Correct. Square root of 1, it's going to be 1. Square root of 0, it's going to be 0. So this is still legal. But the moment you end up with negative 1 inside, you get what is called a non-real answer. So technically, right here, the answer is an imaginary number. Guys, thankfully, I don't have to explain what imaginary numbers are and how they work, other than just me saying imaginary numbers is for negative sort of square roots, okay? And it's important to understand this because it helps you define your domain. And so your domain wants to avoid imaginary numbers, and so x has to be greater than 1, so that this square root is always positive. What do I mean by this? Clearly, we don't like negative a negative value, sorry. We don't like a negative value in our square roots. And so you want to keep this always what's inside greater than or equal to 0. And so, well, whatever, you can leave it as just greater than 0, see? And so here, you do plus 1 on both sides. X has to be greater than 1 for the square root to remain positive. And that is why x has to be greater than 1, see? Alright, that was a little bit of blah blah, but I think it might help for finding the domain down the road. It's important to keep it in mind. Eso, okay? So, for part A, we need to find h exponent negative 1 with a 1 inside. So some of you are probably reading this and saying, that's a derivative. And I would say, excellent guess, I like the energy, but a derivative would look like this. It's with a little bit of an apostrophe, see? Actually, I think it was for number 3. For number 3, you have this apostrophe. So this is for derivative, okay? And this over here is what they call the inverse. Okay, this is for the inverse. And now let's understand how to get the inverse. Let me make a simple example first. Imagine you have, I don't know, y equals 2x plus 3, okay? And so to find the inverse, the first step you're going to do, and pay very close attention to this, the first step you're going to do is you're going to flip the x and the y. So you're going to end up with x equals 2y plus 3. And from here, you want to get y alone. So you're going to do minus 3. Minus 3, it's x minus 3 equals 2y, and then divide by 2. So y is going to equal, just that, x minus 3 divided by 2. See? And so notice, the first step that is very important is change location of y and x. See? If you get very fancy with this one up here is the same as f of x equals 2x plus 3. And this one down here is the same as the inverse of f of x equals x minus 3 divided by 2. And so the last step you can do is sort of like plug in, you know, the f of inverse or f of x. But strictly speaking, this is just y, and this is also just y, just that the y in the version of inverse, okay? So you want to find the inverse, but also plug in x equals 1, okay? And so let's be very rigorous in our approach. All right, something cool about this exercise is that the method is very, let's say, reliable. It's always the same one, yada yada. See? So the first thing you're gonna do, as I said, well, just write down your equation first. So you're gonna have h of x equals 2 divided by square root of x minus 1 plus 1/2, right? Now let's remember that h of x is the same as y. So I'm gonna write y equals 2 divided by square root of x minus 1 plus 1/2, right? Now you're going to do the first more important step, or second important step, whatever. Change the location of y and x. I mean, like, flip them, right? So you're going to end up with x equals 2 divided by square root of y minus 1 plus 1/2. And so from here, technically, because they want an x of 1, you can plug in an x of 1 right away, all right? Or you can do it at the very end. For our intentions, or just for me to explain it more clearly, we're going to plug in 1 at the end, okay? What I'm going to be finding is just the inverse function, and then I'm going to plug in 1. See, I just want to be like a little more clear in my approach. And so from here, Well, clearly you want to get a y alone, but y is in a square root, so it's very hard to deal with. So the first thing I'm going to do is I'm going to try to get y alone, so I can do minus 1 half, minus 1 half. So this goes away with this. You end up with x minus 1 half equals 2 divided by square root of y minus 1. And yes, from here it's sort of annoying to solve this, right? And so what you can do is that you can square everything. See? So if you can square this whole side and you can also square this whole side, right? So what you end up with is that on the left side it's x minus 1 half times x minus 1 half, right? Equals, up top it's going to be 4, and on the bottom it's going to be just y minus 1. So this is a little bit easier to deal with, see? And so from here you actually end up with x times x squared, minus x1 half, minus x1 half over here, right? Plus 1 over 4. All of this equals 4 divided by y minus 1, right? And so because you want to get y alone, or actually, guys, I know that I said first I was going to find the inverse, see? But, and I'm just going to show you, I'm not going to cut this off the video because I think it's important that a lot of times you're doing your math process and you realize, there was a smarter way to do this. So I'm just going to leave it on the video, okay? Point is, I was trying to find the general form, see? But what did I encounter? I ended up with a bunch of x's over here, an exponent. It started getting a little bit weird, a lot of different terms. It would have been harder to solve, okay? So what I'm going to do is I'm going to back it up, Terry. I'm going to back it up a couple steps, and I'm just going to plug in that one that they told me right away. Why would I do this? Because it's going to make my exercise a lot simpler to solve. I'm going to end up with less stuff going around. And so on this step here, I'm going to choose, like right now, I'm trying to do this, but now I'm going to plug in an x of 1. See, so if I plug in x of 1, I end up with 1 minus 1 half equals 2 divided by square root of y minus 1. And so clearly this is way more friendly. You end up with 1 half equals 2 divided by square root of y minus 1. And so from here, what you can do, okay, from here what you can do is that to get y alone, okay, you can multiply, you can cross multiply, okay? So that means I end up with 1 times square root of y minus 1 equals 2 times 2, okay? So that means you end up with square root of y minus 1 equals 4. In order to get rid of this square root, you can do everything squared. Make sure you do it to both sides, so this goes away with this. You end up with y minus 1 equals 16. 4 times 4 plus 1, y equals 17. Now what does this mean technically is that when you have your inverse and you plug in 1, you get 17. Okay, that is what we just did, and that is for part A. Later on, we need to find the domain of the inverse of h. Now technically, I could find the general form and find the domain from there, okay? The thing is, as you guys saw earlier, you end up with a bunch of square roots, you end up with a bunch of exponents, you end up with a lot of different x's. It's pretty hard to solve, see? And I'd rather show you maybe a more direct way to solve it, okay? The more direct way to solve it is that, and this is a general rule, so write it down somewhere, okay, you guys? A general rule that you can say is that the domain of f of x is going to be the range of the inverse. Actually, I'm just going to put range of inverse. See? And something else you can say is that the range of f of x, it's going to be the domain of the inverse. And so if you're trying to find the domain of the inverse for part B, all you need is to find the range of f of x. So what is the range of this equation? Well, first things first, maybe I should have said this earlier, but domain is the possible x values. While the range, you guessed it, is going to be the possible y values. And so what I can do is that I can put up my graphing calculator and say, yo, I need your help once again. I am asking for your assistance. And so you're going to put a fraction here by pressing alpha y equals. Tapping on the first one, you end up with 2 divided by square roots of x minus 1 plus, oops, my bad, plus your fraction right here. See? 1/2. Now, as you can see, these numbers are very small. You literally have an x plus 1/2. So I would suggest that to get the right window, go to zoom and do zoom standard. Okay? Why do I suggest zoom standard in this case? Because zoom standard makes a window of everything equal to 10. Okay? And as you can see from here, it's much easier to see how I should maybe change my graph. So clearly, I only care about positive values, like positive x and positive y, so I can, put an x min of 0, put a y min of 0, and now my graph is only on the positive side. It's much easier to interpret. And so as you can see, what are my possible y values? Well, if I go ahead and graph this for a moment, what we found was something that looks like this, okay? And so clearly my y values, well, they go up to infinity for sure, right? Up here. But do they stop somewhere here? Do they stop somewhere here? And the answer is yes. Now it's very important to understand how far would it go. So are you guys, so as I was saying, if you find the range of f of x, you're going to find the domain of the inverse because they are the same one. And so if you go ahead and graph over here, right, as I showed you, you end up observing, right, that that your function, right, seems to reach an asymptote on the horizontal, right? And so basically your y equals is gonna like grow a lot, right, over there, but eventually it's gonna find a horizontal line here. And so the hard part now is finding what is that horizontal part, and wherever that horizontal part is, you're gonna say that your y values are gonna be everything in between. See? So you're gonna find sort of like that edge, right? Its limit. And so one way to do this, and what they suggest, is that for horizontal asymptotes, I'm actually going to write this, for horizontal asymptotes, put a large value on your table. Why is it this way? Because for horizontal asymptotes, for example, this is, I don't know, y equals 1, y equals 1/2, like, we're about to find out, see? And so the bigger your x value, eventually you're going to find, so that's the value that y never reaches, see? I know that might sound weird, but for now follow the process. Pull up your calculator, go to table, and scroll all the way down. See? Eventually, it's going to be very obvious which y value you're never going to reach. Now, as you can see, you can be scrolling for quite a while. So what you're going to do is that you're going to press this blue button, second window. That way you hit table set. And what this allows you to do is that you see how you have this little triangle table. This is by how much each value changes. So for example, if I put a table of 2, and again I start at 0, and I go to my table, look at these x values. It goes from 0 to 2, 2 to 4. So now your scrolling is a lot faster, right? But you are in the context of a test. So you don't care about your table looking pretty. You just care about the answer. So your table is going to start at 0, but it's going to change by an incredibly large number. Yes, just do it. Incredibly large number. You go to your table, you start scrolling down, and basically by now you're like at infinity. I mean, not really, but you're giving some incredibly large x values. And what y value do you never reach? 0.5. Clearly, you never reach 0.5. You get very close to it, but you're never going to reach it. That is your horizontal asymptote. Your horizontal asymptote is at y equals 1/2. So if you never reach y equals 1/2, that means all of these other values are y is greater than 1/2. And so the range of f of x is y greater than 1/2, and so the domain of your inverse, because it's domain, because it's x values, is going to be x greater than 1/2. This is a math rule you can always apply. I heavily suggest you write this down somewhere. It's very big brain stuff, and it's probably the quickest way to do this. The other way to do this is that you find the OG inverse function. But as you saw, even it's not that I got scared of it, but even I said, like, dude, that would take way too long. You have like a quadratic going around, you have exponents, this or that. This is the more quick way, see? Remember to change your table set, okay? This is the big hint. A lot of the IB is just understanding how your graphing calculator works and all the tools that are inside of it, okay? So, make it start at 0, maybe put it back to 1 for a future example, but, so that you can analyze your graph more clearly. But for finding asymptotes, just put an incredibly large number and it's going to make sense, okay? Even if you put the largest possible. Here I put all the zeros I could. Clearly, y reaches that 0.5, see? So it's never, whatever. Your domain, the range of f of x is 1/2, so the domain of the inverse is the same thing but with an x instead of a y, see? So enough blah blah. For part 6b, you would say that the domain of h of inverse is x greater than 1/2. What is your argument? That the range of the OG one is 1/2. So ladies and gentlemen, that is how you solve number 6. Not that hard, but you do need to understand the procedure of the inverse, okay? Remember, change the location of y and x, and from there, everything just kind of flows. They usually ask for domain and range, and so this tool here is going to do wonders for you, okay? Ladies and gentlemen, that is for number 6, and I hope it helped. Right, so now for number 7, we have done an athlete on a horizontal athletic field throws a discus. The height of the discus above the field in meters, careful, that's our units, after it is thrown can be modeled using a quadratic function of the form blah, blah, blah. Okay, this is a general form of the quadratic function. It's, how it comes. So x represents the horizontal distance, so x is going to be horizontal distance that the discus has traveled from the athlete. A specialized camera tracks the initial path of the discus after it is thrown by the athlete, and the camera records that the discus travels through 3 different points. And those 3 different points are here, and are here. As shown in diagram 1, they are there, and they are there, and they are here. All right, cool. And so for part A, we need to use the coordinates of this first point, the one that I have in green, okay, the one that I have in green, to write down an equation in terms of A, B, and C. So guys, just so that we understand, when they say in terms of A, B, and C, it means that you need to have an equation with those variables inside of it, okay? And so you might have like a number equals blah, 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 A, B, C, okay? This is the main idea. You have equals A, B, C, all right? When they talk about, I don't know, y in terms of x, you want to have y equals blah, 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 x, all right? In terms of A, B, C, you want to have equals A, B, C, all right? So that's the first intuition I'm going to share. And the second thing I'm going to talk about is, all right, so this point that I have in green, this one here, all right, it belongs to what type of function? They first told me that we're talking about a quadratic function, so I can use this equation here. This equation here is technically also in your formula booklet. If you look up the whole thing about slopes and axis of symmetry, here it is as well. Okay, so if you ever forget it, but you identify the buzzword quadratic function, here it is in your formula booklet. Back to the test. So my general form, okay, is f of x equals ax squared plus bx plus c. And so this green point that we talked about earlier is 3 comma 2.82. 3 comma 2.82. And so if you go ahead and plug in this point into the quadratic function, well, let's remember that this 3 is x and this 2.82 is y. And let's remember that f of x is the same as saying that this whole thing is y, okay? And so that whole thing is y. That means you will be having 2.82 equals ax being 3 squared plus b times 3 plus c. And if you simplify this just a little bit, you're going to end up with 2.82 equals 3.39a plus 3b plus c. And so this is for the green point, okay? All right, so that is for part A. Then part B, which is way more points, asks us to use the answer in part A and two similar equations, okay, similar equations, to find the equation of the quadratic model for the height of the discus. Now you guys, this is a classic, okay? Think about it this way. To build a quadratic function, you need 3 different points. Okay, that is the main idea that we're going to draw from this exercise. To build a quadratic function, you need 3 different points. You need 3 different points because, as you can see here, you have 3 different variables. Your variables being A, B, and C. Okay, once you discover A, B, and C, well, I mean, technically your variables X and Y, but once you discover A, B, and C, you can plug it in and end up with a quadratic function. So for a quadratic function, you need 3 different points. For a line, as you can see here, you have 2 things you need to discover. You need to discover M and you need to discover B. So for a line, you only need 2 points because there's 2 things you have to discover. For a quadratic function, you need 3 because there's 3 things you need to discover. And lo and behold, they give us 3 points. And so the version in green is right there. The point that is in blue, I'm going to do it now. So the point in blue is 6, 4.25. So here we're going to be plugging in 6, 4.25. And so if I go ahead and plug in 6, 4.25, you end up with 4.25 equals a times 6 squared plus b times 6 plus c. So 4.25 equals 36a plus 6b plus c. So this is the blue point, all right? And last but not least, we have the red point. The red point is 9, 5.30. So 9, 5.30. So if you plug that in, you're going to end up with 5.30 equals a times 9 squared plus b times 9 plus c. You do a little bit of quick maths and you're going to find that 9 squared is 81. So 81a plus 9b plus c. Okay, this is a b. Looked like a 96 for a second. This is a b. Okay? Yeah. So here I have my 3 fancy equations, okay? And just to be like a little more organized, okay, I'm gonna write them all down like on top of each other. See, so here I'm gonna have the 2.82 equals 9a plus 3b plus c. Here I'm gonna have the 4.25 equals 36a plus 6b plus c. And at the bottom, I'm gonna have 5.30 equals 81a plus 9b plus c. All right, guys. So from here, if you think about it this way, you have 3 equations and you have 3 things to discover. That means you can discover it, okay? And if you discover a value for A, B, and C, you're going to be able to plug into this guy here, and boom, you're going to have the equation of a quadratic model. okay? So as long as you find A, B, and C, you're good to go. Now, from here, technically, if I get very mathy and fancy with you, this is a system of equations. When you have a system of equations, you have to play around with them to get A, B, and C. Now, you have two main tools, you guys. You have the first tool called substitution, and you have the second tool called elimination. All right? I think this video would be insanely long if I show both. So to my liking, I feel like substitution is a little more friendly, okay? But if you see a way to do it with elimination, you do you, all right? So the whole point of substitution and elimination is that you decrease, and this is the key idea, you decrease the number of variables, okay? So notice right now I have, we're gonna call this my first equation, this one our second, this one our third. And so in our starting point, you guys, help me see, in our starting point, how many variables do you have? In our starting point for all three of these, you have A, B, C. So you have three variables, okay? Well, I'm not going to put in parentheses because it might be a little bit weird, but you have three variables, all right? You have three variables in your starting point. But the moment you use substitution or elimination, you're going to see we go from 3 to 2. And that is the magic of system of equations. That is the cool thing about it, if there's anything cool about math. So, for example, this first one, what we can do is that I can end up with C equals something, okay? So let's say that C on this first one, right? Let me rewrite the first one. So the first one is 2.82 equals 9A plus 3B plus C. So if you want to get C alone, you're going to have to do minus 3B minus 3B. That's 2.82 minus 3B plus 9A equals, oh shoot, my bad. So 282 minus 3B equals 9A plus C. And so from here you can do minus 9A minus 9A. Clearly you end up with a C that is alone. So you end up with C equals 2.82 minus 3B minus 9A. And so this right here, I'm going to call it 1 with an asterisk, okay? This is all just so my process is a little more organized, okay? This is not like how you're supposed to do it or whatever. No, this is so that your procedure is more organized. It's my way to do it. I put numbers to each of my equations, and if I change one around, I put an asterisk next to it. And so number 1 asterisk gives me that C is this whole thing, okay? So now I take 1 asterisk and I plug it into the second one or the third one. I'm just going to choose arbitrarily to plug it into the second one. So the first one with asterisk is going to enter the second one. So if I do that, I end up with 4.25 equals 36A plus 6B plus C. But C, ladies and gentlemen, is now this. This is C. Okay, so that means I have plus 2.82 minus 3B minus 9A. Now, hold up. Let's take a breather. Notice, this is a very long equation. This probably looks a little bit scary. But, key idea pulling through. Originally, we had 3 variables. How many variables do you have now? Ah, you only have A and B. So we just passed from 3 variables to 2 variables. Okay, and how did we do that? Through substitution or elimination, in this case, substitution. And so the whole magic of substitution and elimination is that it helps you decrease the number of variables. And eventually, we're going to reach only one variable. So we're going to reach A equals, I don't know, 9, okay? Or B equals 7, because you only have one variable. We're not quite there yet, but we're almost there. So if I combine some of these like terms, I can have this 36 with this, this 36A with this 9A, right? So that means I have 27A plus this 6B with this minus 3B plus 3B plus 2.82, right? And so from here you choose to get either B alone or A alone. I'm going to choose to get B alone. So I'm going to do minus 2.82 to both sides. Bada bim, bada boom. That is a decimal that no one wants to calculate. So I'm going to pull up my graphing calculator. There it is. So my graphing calculator, trusty rusty calculator, I'm going to do 4.25 minus the 2.82. Bada bim, bada boom. 1.43. So 1.43 equals 27A plus 3B. To keep getting B alone, you got to do minus 27A because there's a plus next to it. So that means that 3B equals 1.43 minus 27A. And now if you go ahead and divide by 3 because you want to get B alone, you got to divide everything by 3, right? Golden rule of algebra, something we've learned over these last 2 years of IB, hopefully. B equals 1.43 divided by 3, whatever that is. Okay, so 0.476. Now, if you want to do this in significant figures, or actually, yeah, so significant figures, you would count 1, 2, 3. Do you round it up or keep it the same? You round it up. So we're going to leave it as 0.477. All right. Minus 27 divided by 3, I'm pretty sure is 9. But we all double check sometimes. 9. So 9/8. All right. So from here, we just found that B equals 0.477 minus 9/8. I'm going to call this 2 asterisk. Okay. And so now with 2 asterisk, I'm going to plug it into number 3. So 2 asterisk is going to enter the third one that is untouched. Okay. So the third one untouched is 5.30. Oh, wait. Actually, give me a second. Give me a second. So this is my value for B. This is my value for B. Right. So if I go ahead and take this one. So now the weird step that I just recalled. Okay. So notice how on the one hand you have C equals something, and on the other hand you have B equals something, right? So if you go ahead and plug both of these things into like any equation, right? Let's say the third one, see? So I'm gonna go ahead and put like all into the third one, see? So you do all into the third one, you're gonna end up with 5.30 equals 81A. So I'm talking about this one here, right? 81A plus 9B. Now we did say that B was 0.477 minus 9A, right? And then you're going to have the plus C. But you know that C from here has to be, plus C is going to be 2.82 minus 3B minus 9A. But you know that B has to be this guy. And so, right on that step, you're going to say that it's going to be minus 3 times 0.477 minus 9A. Minus 9A. See? So let's take a moment to really understand what just happened. This is your C. This C that is here, right? And so, and this right here is your B, which is what we plugged in for this, okay? So now, this is an even bigger equation. It looks even scarier, but how many variables do you have? Will you look at that? You only have A's going around. So yes, it looks scary, but now you have one variable, which is A. And that is happiness for a system of equations. See? So notice how the procedure is always the same. You're going to take, I don't know, what I suggest, right? Put numbers to each equation. You're going to take, I don't know, the first one and leave it in C equals terms of B and A, right? So here you have C equals something something B, something something A, all right? Later on, you're going to end up with B equals something something A. And so that means that you can plug both of these things in such a manner that you end up with only A's. Okay, that's the whole idea. You end up with only A's. All right? This is a procedure that you can practice a lot. There's a couple different ways to do it. This is just the one that I suggest. All right? If you see a shortcut, find a shortcut, do your thing. But a procedure that might take a little bit longer but always works is this one. Okay? Anyways, from now we need to get A alone, which is of course terribly annoying. But once you find A, everything else just kind of flows. So for 3 points, I feel this exercise is pretty long. But it's surefire points that maybe take a little bit longer, but you're going to get all 3. Because the procedure is very mechanical. It's always the same thing. So 5.30 equals this 81A that we talked about, plus 9 times this. So 9 times this is 9 times 0.477, 4.293, 4.293 minus 9 times 9a, it's going to give you 81a, plus 2.82 minus 3 times this, so that's going to be 3 times 0.477, 1.43, 1.431, sorry, and times negative 3 times negative 9. So that's going to be plus 27a. And then we have the minus 9a at the very end. All right. So from here, a couple things you can do. This goes away with this. And let's say I combine all of these, right? So you're gonna, when you combine all of these, you do 4.293 plus 2.82 minus 1.431. So that means on the right side, you're going to end up with, I mean, you still have 5.30 on the left side. On the right side, you end up with 5.682 plus whatever is the remainder of these two A's, right? So 27A minus 9A, I'm pretty sure it's 18A, but I'm going to double check because that's how I am. It's 18A. And now you just need to find the value of A. And so to get A alone, you do minus 5.682 minus 5.682. You end up with 18A equals that. So 5.30 minus 5.682. Boom. Negative 0.382. Negative 0.382. If you go ahead and divide by 18 to both sides, you're going to find that A equals, finally, you're going to have that A equals 0.021 negative. So negative 0.021111. If you do significant figures, however, you skip the zeros and you count 1, 2, 3. Round it up or keep it the same, you keep it the same. So significant figures, we're going to leave it as negative 0.0211. So this, ladies and gentlemen, is my value for A. And yes, you might be thinking, all right, oof, finally, so much work, and we got a value for A. Well, yeah, now you got to find B and C. And so some of you are probably thinking, dude, I thought we were done. What the heck? And no, we're not done, but everything that's coming is very easy, okay? Once you find one of the variables, whether it's A, B, or C, it just kind of flows, dude. I'm just saying. For example, here, you have an equation that is B in terms of A. And so if you plug in A, you're going to get B. So if you plug in B into, if you plug in A into this one, right? So you're going to be putting this there, right? You can see that B has to be, that sounded funny. B has to be 0.477 minus 9 times negative 0.0211. So that means that B is 0.6669. So B equals 0.6669. Now, if you do significant figures, you're going to count 1, 2, 3. Do you round it up or down? You round it up. So B is going to be, bow, chicka, wow, wow. B is going to be 0.667. All right. And now, as you can see, we got a value for B incredibly fast. And with these two values, now it's super easy to get C. You can even plug it into one of these and you're going to get C. But just to be a little bit more rigorous, we're going to plug it into this one here. Okay? So if you plug it into this one here, you're going to say that 2.82 minus 3B, and we know that B is 0.667, right? Minus 9A, and we know that A is negative 0.0211. You end up with a value of C of 1.0089. So C equals 1.0089. And if you count three significant figures, you go 1, 2, 3. You do count the zeros because they are after an actual number. Okay? You do count the zeros because they're after an actual number. So 1.00. Do you round it up or keep it the same? You round it up. So significant figures would be C equals 1.0. You guessed it. 1.01. Kablam! And so here are my values of A, B, and C. Now we can plug it into this guy here. And that means that the whole thing for part B just ends up being f of x equals your A, which we said was negative 0.0211 x squared plus 0.667x plus 1.01. If you're asking what did I plug into, we plugged into the quadratic function, which is this guy here, okay? And again, we know that it's this because of this here and because of the buzzword quadratic function, okay? So that is for part B. A little bit long, but a procedure that is always the same. And so in that sense, this exercise is a little bit friendly, all right? Anyways, that is for part B. Then they tell you that a 1.8 meter high wall is 30 meters from where the athlete threw the discus as shown in diagram 2. And we need to show that the model predicts that the discus will go over the wall. And so from here, you can just say, look at the diagram, it's going to go over the wall. And you're done. Just kidding. I wish it was like that. For part C, we have to do a little bit of critical thinking. And so this f of x, right? This f of x, blah, 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 this one here, right? Let's recall that f of x is the same as y, okay? And so that means if you do a little bit of a table, if you plug in x, you get a value for y. And so this is going to give you a bunch of different points, right? In fact, if you plug in 3, for example, you're going to get 2.82. If you plug in 6, you're going to get 4.25. And so you're going to get all those different sets of points. If you plug in 9, you're going to get 5.30. Okay, why am I saying that? Because you know that the distance from 0 to the wall is 30 meters. And so which x value does this wall have? This wall has an x value of 30. So here, you know that you have an x of 30, but you don't know the height, okay? Now the height you would be finding is the height of the discus. So you're going to be finding out just how above the wall the discus is flying, right? And if you happened to get a value that is below the wall, then you would say, okay, it's going to crash into the wall, all right? Pretty straightforward, not that complicated. identify that you need to plug in 30 for x and compare it to the 1.8 meters of height. All right, so if our y value is bigger than 1.8, it's going to fly right over. If it's lower than 1.8, it's going to hit the wall. If it's at 1.8, it's going to hit the wall at the very top. Okay, so go ahead, take your calculator, and we're going to be plugging 30 for x. Okay, so you plug in 30 for x, so negative 0.0211, 30 squared. We double check that it's correct. It looks fine by me. Plus 0.667 times 30 plus 1.01. And so here we see that you get a value of 2.03. And so 2.03, I mean, the height here at 30 is 2.03. And just so we understand what I mean by this, it's the point that it's in red. Okay, so the discus is going to be at 2.03. And is this above the wall? Well, how tall is the wall? The wall is 1.8 meters high. And so for part C, you're just going to say, oh, at f of 30, we got 2.03. And 2.03 is higher than 1.8, the height of the wall. And so this is a way that you show that the discus will go over the wall. And so writing this is good enough, but if you want to like whatever be more rigorous, you can also literally say hence or therefore the discus shall go over the obstacle. All right, just kidding. Say it as you want, but you can say therefore the discus will go over the wall. All right, that is how the answer key leaves it. All right. And I want to point something out that's very important, that is a test-taking strategy, which goes beyond number 7. It goes about how to approach these exercises. So the day of the test, you might be reading, or let's say the day of the test you face this problem, okay? So you face this problem, you say, okay, part A is worth 1 point, and it's pretty easy because you write just one equation. Part B, as we saw, takes way longer. Okay, you identify that it's about finding the equation of a quadratic model. You know you can do it, but you know you take a long time, right? And so maybe it's not the ideal to do it right away, but notice, part C was just plugging in 30, and it took me probably like 30 seconds. I mean, I spent some time explaining it, but the day of the test, you're going to say, plug in 30, bada bing, bada boom, 2.03. It would have been way faster. See, this video is longer because I'm explaining everything, but the day of the test, it would have been pretty fast. And it's some pretty fast 3 points. And so this is something you have to consider, right? Yes, part B takes a long time. And yes, you know, it's maybe not worth the points for the amount of time it takes. But part C is super fast. And part C is worth 3. And you can't do part C without part B. And so really, like, if I were to make this like more fair in terms of grading, I would probably say that part B is worth like 5. And I would make part C worth 1. Because in terms of time, that is a better reflection of how this score should be done, in my opinion. Okay? Point is, you read this and you say, okay, part B takes a long time, part C is super fast, and so if I do part B, part C is going to net me a lot of points. And so this sort of analysis can help you identify which exercise you do first, which exercise you do second. Always do what you feel comfortable with first. This is not just a test of your math skills, this is a test of your test-taking skills. It's a test with time, okay? You don't have all day to do it. Might as well prioritize the stuff you know first and whatever nets you the most points first. All right, so just keep in mind what I just said. It might help you down the road. Last but not least, for part D, we need to find the horizontal distance that the discus will travel from the athlete until it first hits the ground, according to this model. And so basically, looking at this diagram here, it's, all right, so we're talking about it hits the ground, so we're talking about this point here, all right? And so essentially from here, you need to find what they call, because this is an XY, you need to find what they call a x-intercept, all right? And so there's a couple different ways to find the x-intercept, but the main idea that we need to immediately understand is that an x-intercept is x, I mean it's something, comma 0. For a y-intercept, it's 0, comma something. All right. So on the one hand, what you can do is that you take your equation and you equal it to 0. So you're going to have 0 equals, because your y is 0, right? So 0 equals negative 0.0211 x squared plus 0.667 x plus 1.01. All right. And from here, you have a couple of tools. All right. You can do the famous maybe factoring, although factoring here seems incredibly hard. You can do factoring. You can use the quadratic function. All right. B squared minus 4ac divided by 2a, which, by the way, let me just check if it's in the formula booklet. And you have graphing, okay? For today or for this one, I'm going to probably just do graphing. Let me look at the formula booklet to see if the quadratic function is here. Quadratic function, zeros maybe. I don't think it's here, actually. Probably would have showed up. Anyways, so it's not even here. See, this one, I don't think it's in the formula booklet. I don't recall it, at least. Point is, this one helps you find the x-intercepts, all right? And so you literally plug in A, B, and C, and it helps you find the x-intercepts, all right? You've probably seen that in class, so I'm not going to go over it now. The most efficient way, in my opinion, to do this is just to graph it. So go to y equals and put this whole thing. So negative 0.0211 x squared plus 0.667x plus 1.01. Now, guys, a lot of you might be thinking, dude, every time I do graphing, like, my window is always, like, so messed up, and I just don't know what's going on. I don't like graphing because I can't get the right window. Guys, it's not incredibly hard, okay? A lot of times by context, you can get a better window, all right? So this is a quick 101 on how to get a good window on your graph so you can use all the functions you need, okay? And find all the intersects and all the good stuff. See? The first step you're going to do is, well, of course, plug in your equation into your y equals. The second thing you're going to do is you're going to press zoom and go to what is called zoom fit, okay? Zoom fit is especially good for finding intersects, okay? Here we're trying to find a 0, okay? So it's an x-intercept. Zoom fit might not get that, but zoom fit is really good if you're trying to find an intersect of like 2 lines, okay? So anyways, I can put zoom fit, and from here, I don't see the x-intercept, you're correct, but I get a better idea of what my window is looking at, okay? And so now you could go to window and change what you need to change. Now, first things first, by context, the window, by context, you can figure out what your window should be, all right? So first things first, they talk about this wall, right, that is 30 meters, right? So, sorry, at 30 meters, you have this wall. So at an x of 30, you have this wall, and the discus goes over the wall, and so your window should probably be like around here, right? This should be your window. And so an x of maybe 50 would make sense, right? So just by context, it makes a little bit more sense. Your x minimum should be 0 because you only care from where the athlete throws the disc, okay? Now, thankfully, zoom fit helped me put x at 0. But if it didn't, now you know. See, you only care about positive values. Y minimum, well, it puts it at 1.01 because that is your y-intercept. But I'm going to put it at 0 just that it looks pretty. And your y max, well, the 6 looked fine. It looked like where the maximum was. But just to make it look pretty, I'll put 10. See? So notice, I know some of you might be thinking, dude, you're just like pulling these numbers like whatever from wherever, right? And I'm saying no. I look at the context and I put a bigger value. Okay, that is another hint I'm going to give you for a nice window. Put values that are overly big. Okay, if you want to have a perfect graph, I would probably put an x max of, I don't know, like 40. But I just want to see the intercepts. I just want to see where it crosses lines. Put a number that's a little bit bigger. See? So now you graph it, and yes, it's a little bit bigger. Yes, maybe it's not as pretty, but you see everything you need to see, right? I'd rather have my graph look like this than be fighting to have the exact value and stuff like that, and then, oh, like my x is there, but barely, I don't know. I'd rather have you go overboard and calibrate from there. Okay, that is my main message. Go overboard, calibrate from there. And so from here, I can do second calc, find a 0, it literally says 0. Whenever you use the 0 function, it's just for finding the x-intercepts, okay? And so the 0 functions for x-intercepts, here it asks for left bound, so I'm going to put that around there, and then it asks for right bound. I'm going to make sure it's way to the right of my x-intercept, and now you can guess, right? Let's just understand what I just did. So when you do the left bound and the right bound, which I did like somewhere here and here, right? Notice the little arrows at the top of my graph, the same arrows I'm drawing here. What you're asking your calculator is, okay, this is my left, this is my right, scan in this area, find all the zeros you can, and with the guess function, you pick your 0. Now in this case, there was only one 0, so the guess function is going to give you the only 0 that there is. But it's not guessing because your calculator is dumb. It's guessing like, okay, pick the 0 you want. But in this case, with the bounds I chose, there's only one 0, and there it is. It's at x equals 33.05. And so, if you get very rigorous in this approach, you would say that the horizontal distance is going to be 33.0. 33.05. All right. And so technically, well, because we use significant figures, our answer is a little bit different from the mark scheme. But as long as you're consistent, you're going to get full credit. I want to point something out just so that you know. Remember how I equaled it to 0? Okay, this is a key idea. And this actually gives you one method point. And the other point is an answer point. All right? So be very careful. This whole idea of equaling to 0, I know that I said it for us to understand that, oh, it's an x-intercept, right? And so you want to equal it to 0. But it gives you a method point. So write it out, okay? Part of writing it out is that you're telling the guy grading, I know what I'm doing, okay? And even if you don't know what you're doing, it's a method point, so do it, okay? Might as well write it. It's going to get you a method point, and that is, ladies and gentlemen, for number 7. And just to clarify, if you look at the answer key, you're going to see over here that our answer was a little bit different, right? And part of this is because there's a lot of different ways we could have gotten our answer for our quadratic, right? You could have done it like us, doing the significant figures, or you could have put in like the whole entire values, or you could have been one of those weird guys that does fractions, okay? I'm a weird guy too, don't feel offended. I also like fractions, but I do it in decimals because, you know, most people prefer decimals. Anyways, point is, because this one has like the ultra mega specific decimal range, okay, this one is more accurate, right? It doesn't mean that your other answer is wrong using the significant values. I mean, yeah, with the significant values, but you're going to be off by a little bit, right? And so the answer key, yes, it has it at 33.0. We got 33.05, but really, because we followed our method, because we followed our answer from before, you're going to be okay, all right? I'm just saying, if you're looking at the answer key and you're freaking out because you're off by a little bit, you're off by a little bit because the significant values make it a little less accurate, okay? But that's fine. As long as you're consistent, you're going to get full credit. Trust me on that. Don't worry. For part D, the answer was 33.05 meters. Make sure you showed your method point as well by equaling to 0 because it's an x-intercept. All right, guys, that is enough blah blah by me, and that is number 7. All right, and now we have number 8, which is a very menacing problem. It probably looks very scary, but it is exactly in doing things we fear that we grow the most. So let me erase that. I was brainstorming a little bit because even for me it was like, damn, what do I have to do? But let's go piece by piece. We have this fancy diagram that shows a map containing a long winding road, okay, a long winding road passing a lake. The shape of the road can be modeled by the function blah, which is actually what is happening in this whole thing over here. Okay, so all of this is the road, and yeah. The local hospital is located at point H conveniently, which has the coordinates negative 2, 16. So you always want to make sure that what they give you is in your diagram, or if not, you put it, so that negative 2, 16 is right over here, all right? And to save time during emergencies, the local community is planning the construction of a bridge over the lake. That is a wonderful idea. And the bridge will be built such that it is normal to the road at point H and will connect the hospital to point G. Now, I'm immediately going to talk about this because this is an incredibly important buzzword, normal to the road. I'm sure a lot of you are reading this and thinking, or maybe not thinking at all, and you're just kind of like, what? What is the normal to the road? What is the normal to a curve? Because later on, they talk about the line normal to Rx. What is this? See? All right, guys, this is intuition. Imagine you have whatever sure a function that looks like this. So this is going to be f of x, okay? Now let's say that on your plot, this is x and this is y. And first, in order to understand normal, we need to understand tangent, okay? A tangent is something that touches at one point, and like never again, see? Now, depending on your graph, it might touch again, but essentially a tangent is that it touches the line at one point. Okay, that's the main idea. It touches only at one point. So for example, let's say that I have a tangent at, I don't know, tangent at x equals 5. Okay, so in this graph, again, I'm just making up the numbers, but so we understand the idea, at x equals 5, maybe it's like, I don't know, right here. Okay, so here you have an x of 5, all right? And so a tangent to the curve f of x at x equals 5 would be right here. So right here you have an x of 5. All right, so right there it's going to pass through my line. And here is the tangent. All right. The cool thing about this tangent is that the slope it has is the same slope that f of x has at that point. Okay. Anyways, this is the tangent. All right. If you want to talk about the normal, it's related to the tangent because the normal is actually perpendicular to the tangent. So the normal, and this is something you should be writing down. So the normal is perpendicular at that point. All right. So for example, the tangent has a slope of, I don't know, a slope of 2. That means that the normal in this case is going to have a slope of negative 1/2. Okay. How did this guy on YouTube just do that? He just did it because for perpendicular slopes, okay, slopes that are perpendicular to each other, perpendicular slopes, you're going to have that the first one times the second one equals negative 1. All right. But more intuitively, you can say that the first one is going to equal the second one flipped and times a negative. And so the first slope is going to be the second one flipped times a negative. So if you ever want to find the perpendicular slope, you're first going to flip it and then multiply by negative 1. Okay? So those are the two steps you have to do to find perpendicular slopes. So for example, if you have a slope of 2, first you flip it, then you multiply by a negative. There's your slope. So if this is my m1, this is my m2. Just to make another example, if my slope of the first one is negative 3 over 4, well, first you're going to flip it, you keep the negative, and then you multiply it by a negative 1, so it would be negative times negative, 4 over 3. That means you end up with positive 4 over 3. So if your m1 is negative 3 over 4, and you know it's perpendicular, the slope that's perpendicular is 4 over 3, okay? So for finding perpendicular slopes, you flip it and you multiply by negative 1. This is important because the normal is whatever is perpendicular at that point, okay? So usually we think about it as finding the tangent and then finding the normal. But if they ask for just the normal, what you have to do is find the slope at that point, okay? And that can help you build the line, all right? Anyways, enough blah blah. Let's jump into the exercise. And so for part A, they ask something quite special, okay? They ask us to use our graphing calculator to find the value of r blah, parentheses, -2. Now let's understand what blah means, all right? So this blah is saying derivative. All right, so you need to find the derivative, basically, of this equation up here. Now, finding the derivative of this equation up here can be a little bit hard. Okay, it can be a little bit hard because, as you can see, you have something to the power of 3. It's a parentheses. It can be a little bit hard to follow. And yes, I have a couple tips and tricks to overcome that. All right, and so the first thing I would do is that I would, well, make space down here, of course. So I'm just going to erase a little bit of what's going on here. And notice that at the IBAISL level, what we have for derivatives is only the derivative of an exponent. Okay. Meanwhile, HL has a bunch of other derivatives, so we can dedicate our time to laughing at them because we don't have to learn so many. But we only have to learn derivative of an exponent. See? And so as you can see, the intuition is that you have an x to the power of n, right? And this n, what does it do? Well, it goes down in front, as you can see here, and it gets subtracted by 1. So, in other words, derivative exponent means that you multiply the exponents in front, or so to say, and subtract the exponent by 1. Okay? So if you have, say, x squared, that means you're going to end up with the 2 in front and the minus 1 up there. So 2x to the power of 1, which is the same as 2x. See? Just to give another example, x cubed is going to be 3x, 3 minus 1. So 3x to the power of 2. And last but not least, imagine you have, I don't know, x to the power of 4 divided by 3. That means you're going to do 4x to the power of 3 divided by 3. So that means you're going to end up with, oh, well, actually, yeah, that's it. So the step in between that I should have done is 4 minus 1. I end up with 4x to the power of 3 divided by 3. If you ever have something on the bottom, make sure you first put it on top. So first you put it on top like this. You make the exponent negative, and now you do the derivative, okay? And now you end up with something that looks like this, and you can put it back on the bottom, all right? I have a video that talks a little bit more about, derivative of an exponent. I go more into depth into why you flip it, why it goes negative. But for now, you can keep that intuition, see? So the moment you're facing this sort of problem up here, and you need to do the derivative of this, I'm pretty sure there's a way to just do the derivative from your calculator and like solve it right away, okay? The thing is, I would rather show you like the manual way to do it, just so that we also practice a little bit derivative of an exponent, and because I think it'll be more useful for whenever they ask you to find the derivative of an exponent, okay? So my OG equation is x plus 2 cubed plus 3x squared minus 2x. See? And so before doing the derivative of an exponent, I really don't like this cubed here. See, so I'm going to try to get rid of it. And the way to get rid of it is that you're going to express x plus 2 3 times. Because that is what the 3 is doing. The x plus 2 is multiplying by itself 3 times. So make sure you keep the parentheses. Everything else stays the same. So from here, I can kind of like distribute considering just these two. Okay? So this times this is going to give you x squared plus 2x plus 2x plus 4. Okay? And so all of this is still being multiplied by x plus 2. And I still have the thing on the outside, 3x squared minus 2x. Okay? And so now you need to distribute again, which again is going to look a little bit weird. You're going to end up with a very big sort of equation, but as long as you follow the process, everything is going to be okay. So if you distribute again, that means that this x is going to multiply, or actually before that even, notice I can combine this 2x with this 2x. So I end up with plus 4x, okay? So that makes it a little bit more friendly. And so from here, I like to think about it as this x multiplying these 3, okay? So if that's the case, you're going to end up with x cubed plus 4x squared plus 4x plus this 2 multiplying the 4 and the 4x and the x squared. So that means you're going to end up with plus plus 2x squared plus 8x plus 8. All right? So take a moment, do it yourself, and really understand what just happened. Okay? And you still have plus 3x squared minus 2x. Now, because none of this is being multiplied anymore, right? Here you had a bunch of multiplication with parentheses. Now there's big parentheses. There's nothing being multiplied outside, so you can just go boom, boom. You can start combining like terms. So r of x, well, think about all the things that have an x to the power of 3 in them. There's only one, right? So bada bing, bada boom, you end up with x cubed. What are things to the power of 2? Well, this one, and this one. So it would be 4x squared plus 2x squared plus 3x squared, which gives you 9x squared. Okay? And now you think about the ones that have only x, which is this one, and this one, and this one. So it would be 4x plus 8x minus 2x. So that would be 10x. And last but not least, the plus 8. So now you rewrote your equation of r of x in a way that makes it easier to do the derivative. So if you do the derivative from here, you're going to find that for this first one, you have 3 in front, and then the x has the 3 on the exponent has a minus 1, okay? For this next term, you're gonna see that you have 9 times 2 with an x to the power of 2 minus 1, right? And for this 10x, you're gonna see that you have just 10, okay? And what happened? The x multiplied with the 1 in front, and you have a minus 1. So actually, if I'm very, very rigorous here, I would end up with 10x to the power of 1 minus 1, okay? And this last one, the plus 8, actually disappears. And the reason it disappears is because technically, if I get very hardcore mathy with you, technically there's a hidden x to the power of 0 here. Remember that anything to the power of 0 is 1, okay? So technically there's an x to the power of 0. This is multiplying in front, so anything times 0 just turns into 0. The other way you can remember it is that anything that is just a number that is alone without a variable next to it is going to disappear in the derivative, okay? So that is just going to disappear. Let me rewrite everything so that we're a lot happier, and you're going to end up with 3x to the power of 2 plus 18x plus 10. Okay, so this is the derivative that I had to do. A couple steps happened beforehand, but I think it's good practice. I would rather show it to you this way. And so now you need to find the value of the derivative, right? When x is negative 2, okay? So if I go ahead and plug in negative 2 here, that means I'm going to end up with 3 times negative 2 squared plus 18 times negative 2 plus 10. So that means over here, if you plug this into your calculator, or actually you don't even need to put it into your calculator, you can end up with 3 times 4 plus 18 times negative 2, which gives me negative 36, if I'm not mistaken. That sounds about right. Plus 10. So r to the power of negative 2, the derivative of r with an x of negative 2 ends up with 12 minus 36 plus 10. So that means you're going to end up with, let me make a little bit more space because I write a little bit big. So it's going to be 22 minus 36. And now it's very obvious that it's negative 14. Okay? So with my function as a derivative, when x is negative 2, you have a value of negative 14. Now we need to understand for the context of the problem, it's very important. I mean, this is part A, but for the context of the problem, we need to understand what a derivative even does, okay? So originally, when you had r of x, okay, let's say you would plug in an r of negative 2 in the original one, right? What you end up with is a set of points, okay? Basically, if you plug in negative 2 here, you're asking your function, when x is negative 2, what is y? Okay, and when you plug in negative 2, you actually get a y of 16, okay? So what I'm trying to tell you is that, yeah, positive 16. So what I'm trying to tell you is that in the OG like scenario, you plug in an x, you get a y as a set of points. And when you have the derivative, okay, now it's a little bit different because here, actually what you're asking your function is when x is -2, what is the slope? Before it used to be what is the y to get an x comma y, all right, to get a set of points. But now you're asking what is the slope? So when the derivative of r is -2, the slope is -14. And so you know that a slope of 1 looks like this. You know that a slope of -1 looks like this. And so a slope of -14, damn, dude, that's gotta be something very, very inclined. Something like this. Which actually makes sense because at the point -2, which is h, at the point of -2, which is h, what is the slope? It's going down big time. It makes sense that the slope is -14. Okay, so this is just a little bit of context, and this is actually important to keep in mind for part B. For part B, they tell you to find the equation of the line normal to Rx at the point H, which can be used to model the new bridge. Now, quick pop quiz. What was the normal? Okay, the normal is perpendicular to the tangent. And so if you have a tangent here, then this is the normal, right? If the tangent has a slope of 2, the normal has a slope of -1/2. Because you flip it and you multiply by -1. Technically, this line that I put in orange is like a tangent. See, if I zoom in a lot, it would touch only once. But here's my tangent. And so this tangent has a slope of -14 as a tangent. And so what is the slope of the normal? The slope of the normal is going to be that you flip it and multiply by -1. So -14, you flip it, so 1 over 14, and you have a negative times a negative. So that means the slope of the normal, the slope of the normal is positive 1 over 14. So the slope of this line here, that is in green, is 1 over 14. And I figured that out all because of normals and tangents and stuff. You can also figure it out because from part B, you needed something from part A. So why would they ask for the derivative just at -2? Well, because it helps you find the slope of the normal. Okay, so there's a reason part A was so specific. It's because for part B you needed it, and that is something that happens a lot in the IB. Not always, but in this case it does. Okay, so that is a hint for what we have to do. This is a slope that can help me find the line to the normal. Okay, and from here you need to use an equation of a line. Okay, because a normal is a straight line, and there's a lot of equations of a line that you can use. And so you go to your formula booklet, okay, and you go to equation of a line, all right? Of course, you're going to run into a bunch of different stuff, and actually, it's not equation of a line. It is, let me find it, equations of a straight line. There it is. It's equations of a straight line. And so as you can see here, there are 3 different equations of a straight line, okay? You have y equals mx plus c, which is like the classic, okay? It's your Big Mac. It's what you want to go for. Then you have this weird one that when you're feeling it, you're gonna go for that. And then you have the McNuggets, the old reliable. Okay, the McNuggets is what you call the point slope form. All right, point slope form are McNuggets, the usual go-to, is super useful because it is the most ideal for creating an equation. All right, a lot of times they ask for your answer to be in this form or in this form. But what a lot of people don't have clear in their mind that the best one for creating an equation is this last one. It's the point slope form. For creating an equation, it's the one you want to use. And so what does it ask for? Well, let's look a little bit more closely. Okay, this is way, way more closely, but ain't that the point? Understanding things in detail and with love, right? So here, what do you actually need? Well, y and x is not going to change. I mean, it's your variables, right? So that is going to stay put. That's not what you're interested in. What you need to discover is y1, m, and x1. And so y1, x1, much like in this part here, is really just a set of points. And so x1, y1 is literally a set of points. So if you have a set of points, and if you have m, which is the slope, you can use this equation. As long as you have a point and a slope, you can create the equation of a line. So we go back to our fancy test, and we say, okay, so this guy on YouTube told me that for creating an equation, you gotta do the McNuggets. It's y minus y1 equals slope times x minus x1, all right? So what is a point you can use for the green line? Well, you know it's gotta touch the hospital, so a point you can use is -2, 16. And you know that it is the normal at point h. And you know that the derivative at point h gave you -14. And so the normal of that, as I mentioned earlier, is positive 1 over 14. And so this is the point I'm going to use, and the slope I'm going to use is positive 1 over 14. So if I plug all of this into the McNugget, into the point slope form, the best equation for creating lines, you have y minus 16, because this is y1, this is x1, okay? Y minus 16 equals your slope, parentheses x minus minus 2. Now minus minus 2, of course, if you hate to hate, you are a lover, so plus, all right? So y minus 16 equals 1 over 14x plus 2 over 14, right? So now you can do plus 16 to get y alone, and boom, with this, you reached the Big Mac, okay? This one is the one you usually want to reach, just because it's much easier to sort of like interpret. Strictly speaking, for the answer key, you can just leave it as the McNugget, but for us to understand that better, we're gonna leave it in this last form, the Big Mac. Y equals 1 over 14x plus whatever that is as a decimal. See, so we're gonna have 16 plus our fraction pressing alpha y equals, and then pressing the first one. So alpha y equals, and the first one is gonna give you 16 plus the fraction, which is we're gonna call 2 over 14. So that gives me 113 divided by 7. So if you want to leave it as fractions, you can. There it is. If you want to leave it as decimals, you can just leave it as decimals by finding the value of each, right? Like that, and this for the slope, okay? So two different ways to express the same thing. I'm going to leave it as fractions because I'm a nerd, but to each their own, okay? You actually get full credits, just so you guys know. You actually get full credits even from here, okay? Even from here, you get full credits. I just like to reach the last step because it helps down the line, okay? Talking about down the line, part C tells you to determine the length of the bridge, okay? And so reaching a y equals like this can be a lot more friendly, all right? And so for determining the length of the new bridge, there's a couple different things that we can do, okay? Now, we need to understand that we need to find from G to H, okay? That is our main goal. But the main challenge that we're facing is that you have no idea what G is, right? And so once you find G, everything else is going to flow, okay? So let's take a moment and see how we can do that. All right, so what I think is the ideal to do this, okay, is that because you're going to find point G, technically, you want to find the intersect of your green line, which is the normal to the curve from part B, and the OG, which is the road, okay? So if you equal the road to your equation, you're going to find where it intersects, okay? The thing is, you're probably going to find quite a few intersects because technically the line to your normal is like this. And so you need to identify which of these is point G. All right, so the main idea, all right, that you can sort of employ is that technically you are doing your normal to the curve equals Rx. All right, Rx being the line that we have in pink, this whole thing here. All right. Now, of course, if you do that by hand, you end up with something that looks like this: x plus 2 cubed plus 3x squared minus 2x equals the normal to the curve, which we said was x divided by 14 plus 113 divided by 7. And so if I tell you to find x from here, you're probably going to look at me and tell me, dude, what the heck? I'm going to take 4 million years to do it. And I'm going to say, yes, depending on how you do it. Okay, so if you try to do it by hand, you're going to find 3 different x values, and you have to find which of these x values is g. There's a couple tricks to do that from here, but because we have a graphing calculator, I think it's way faster to do it like this, okay? So to do it like this, you can go to y equals, okay, and put both equations. So on the one hand, I'm going to put rx, which we know is x plus 2 cubed plus 3x squared minus 2x. And then we can put the equation of the normal to the curve. So the normal to the curve we said is this guy here, right? So you're going to put, well, a fraction to make it more friendly. So alpha y equals, so 1 over 14x plus, fraction again, 113 over 7. And so from here, right, you can now graph it. Now notice, before we graph, a lot of people have trouble handling the window, okay? So I highly suggest that before you press graph, first press zoom and then go to fit. Usually, this helps you capture the key points in your graph, okay? Any intersects, any maximum, usually it helps, or at the very least, you're gonna have a better idea of how to handle your window. And so there is clearly like the road, and down there, as you see, was the line, okay? The line of the normal to the curve. Now, clearly my window is messed up, okay? So this is one of the scenarios where zoom fit did not help as much as we wanted to, and okay, of course, my y max is like, for some reason, like 14 million, whatever, okay? So, a lot of people come to me and ask me, dude, how do I get the right window? The window is so hard, I don't understand, blah, 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 etc. Here you have to do a lot of critical thinking, okay? So consider this. What point do you know exists on your graph? You know that the point negative 2 comma 16 exists. So you want your window to be sort of in that area, okay? So if this is negative 2, how much do you think is this? Well, it's probably going to be like, I don't know, negative 6 or something like this, right? And so just to play it safe, I would do negative 20. And your maximum, well, maybe 20 plus that 16. We're going to leave it at like maximum of 40, okay? Oh, wait, we're talking about x values, my bad. So yeah, my x max, I would make it 30. And my y min, I would make it 0. And my y max, I would make it 60, okay? And so again, you gotta play it by context, look at the points you have, and overshoot it. Overshoot it in the sense that make your values bigger than what maybe they should be. And you're gonna end up with a graph that maybe is not so pretty, but you should see all the intersects you need. Will you look at that? So again, it doesn't look pretty, but I see all my intersects. Okay, there are my 3 intersects here, here, and here. All right. And now that I got a bit better picture of what's happening, I see that all these x values are useless on the right side, right? So I can make my x a lot smaller, maybe make it 5. And now I get an even prettier graph, see? And if you keep try-harding, you can even say, okay, these x values on the left side, on the far left, are kind of useless. So you can do your minimum, I don't know, 10. And that is how you handle your window, okay? Overshoot your values by some context point that you have, and from there work it out. Now clearly, the only intersect we want is the one on the far left, all right? How do you find it? Well, you can use your intersect function. So you can go to second, press trace so that you hit calc, and here you have a calculate function. I mean, fuck, my bad. You have an intersect function. And so from here, it asks for this first curve and the second curve. Now, usually it's going to pick it for you, but in case you have more than 2 curves, you might have to play around. How do you go from one to the other? You press up or down. Okay? Left or right is for traveling the curve. Up or down is for switching the curves. So usually your calculator knows what's going on. You're going to pick the first one. You're going to pick the second one. And here you have guess. Now guess is not that your calculator is dumb and needs to know the intersects. Guess is that it's like, okay, which intersect do you want? So here you have 3. And just so that we're on the same page, this one in the middle is the hospital, negative 2,16. And so point G is to the left of that. So we're going to do calc intersect again. Make sure we're picking the right curves. Whoops. And now we're going to guess all the way over here. And now we got the value of G. And so the value of G is that. Doesn't look very pretty, but it is what it is. So G, we know is, so G is negative 7.5399. And, comma, sorry, 15.6042. 15.604. All right, and so from here, you know that G is this, and you know that H is negative 2,16. All right? That is all you know. And you need to find the distance between these 2 points because that would be the length of the new bridge. The length of the new bridge is the distance from green to green. How do you find the distance from these 2 points? This is when knowing or being familiar with the formula booklet goes a long way. In the formula booklet, or better said, the day of the test, you're going to be walking with, I don't know, 2 years of experience in this thing called IB, 2 hours of sleep, a pen and pencil, a whole lot of motivation to do well, a couple YouTube videos that you saw from this guy on YouTube, and your formula booklet, and your graphing calculator. So it's very important that you understand all these tools to their depth because they're a tool they can use the day of the test. And so once you are familiar with the formula booklet, and I insist, always practice, always study with it, get familiar with it, you're going to immediately realize, so there's the distance formula. Distance between 2 points, right? And so this one is between 2 points that are x, y, z. But you also have one that is distance between 2 points of just x and y, okay? So I'm going to go ahead and write that down over here. D equals square root of x1 minus x2 squared plus y1 minus y2 squared. All right? And so from here, I just have to plug it in, okay? If you are the type of person that really likes significant figures, which is my case, okay, I'm going to count 1, 2, 3, see if I round it up or down. I round it up. So over here, I have negative 7.54, okay, just so that I don't plug in crazy numbers anymore. And then over here, I count 1, 2, 3. Do I round it up or keep it the same? I keep it the same. So 3 significant figures over here is 15.6. Okay, so these are the 2 points that I'm going to be plugging in to my formula right there. So technically, I end up with D equals square root of, well, pick which one is your first point, which one is your second point. I'm just going to arbitrarily say that this one's my first point, G. So it's going to say x1, y1. This is going to be x2, y2. I strongly suggest making the small step of writing this so that you don't get confused when plugging in. Anyways, I end up with x1 being negative 7.54 minus x2, which is 2, so minus minus 2, ends up being plus 2, all right, squared plus parentheses y1, which is 15.6, minus 16, which is y2, squared. And so all of this square rooted gives me what I want. So technically, I can just plug all of this into my calculator right away. And as long as I'm organized in how I do it, I can do it all in like one step, you know? So 15.6 minus 16 squared, all right? Go ahead and press enter, bada bim, bada boom. You get 5.554. Okay? If you count significant figures, you would say 1, 2, 3, round it up or keep it the same, 5.55 kilometers, all right? So that is the distance that your bridge has to traverse, 5.55 kilometers. I think this exercise is probably scary for many because it has a crazy like diagram on it. But honestly, once you understand the intuition of what is the normal, okay, everything just kind of flows. Okay, remember that the normal is perpendicular to the tangent. Okay, so if they ask for the normal at -2 at point H, you know that the slope there has to be perpendicular to the original one. Okay, and with all of that, you can determine the length of the new bridge. You do have to be a little bit creative to find point G, but again, that is just being kind of savvy with your calculator. Okay, get familiar with the calculator. Notice that yes, you could have done it like this and spent a million years trying, or you can just graph it, play around with the window, and intersect appropriately. Also notice how getting the right window is not always easy, but you don't need it to look pretty. Okay, you just need to be able to see the intersects. In fact, back when I had a larger window, this was already good enough for finding the intercepts. See, I just want to show you guys, back when my window perhaps wasn't so pretty, I could still see all the intersects. And even from here, I can do calc intersect, all right? So I left the window more pretty because of course I'm making a video, like I gotta do it, right? But for you, really this is good enough. And so you do guess over here and you're gonna get what you need, all right? You don't need your graph to look pretty. You just need to see where the key points occur. You need to see where the intersects occur. And with that, your calculator is happy and so are you. Ladies and gentlemen, that is for number 8. And that is all I'm going to do for you today, at least for now. I hope it helped, and I'll see you around. All right, and now for number 9, we have that Mrs. Whitehouse is a chemistry is a chemistry teacher. After grading her final exams, she creates the following box and whisker diagram, okay, to compare the grades of her two classes. So class A is this box and whisker diagram, and class B is this box and whisker diagram. And we need to identify which of the following statements notice must be true according to the box and whisker diagram, and to indicate our choices by placing tick marks. So, ka-ching, 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 on the following table. All right. And so before we jump into the table, we really need to first understand the box and whisker diagram, what it's telling us, what it is. Okay. In any box and whisker diagram, you guys, in any box and whisker diagram, you will have, actually, technically, it's like this. Yeah, it's like this. So in any box and whisker diagram, you're going to have this being minimum, so your smallest value, and this being maximum, okay? And all of this is, of course, being expressed on a number line. So, for example, this is 0, 1, I don't know, 2, 3, 4, 5, 6, 7, 8, 9. So I'm just making these numbers up, okay? So from here, you know that the minimum is 1, and your maximum has to be 9, okay? Well, what is in between? This right here is your Q1. This is your Q2, which is the same as median. Okay, a lot of times it just gets expressed as median. And this one over here is Q3. What the heck is Q1? What is Q2? What is Q3? Q1 means quartile 1. Okay? And so if it means quartile 1, well, it's in quarts, right? And so quartile 1, it's your first 1/4 of your data. So your first 1/4 of your data is 1 divided by 4, which is 0.25. So your first 0.25 of your data is your first 25%. Ladies and gentlemen, your Q1 is your 25th percentile. So Q1 is 25th percentile, which you can think about it as like your 25%, okay? Now notice, following this logic, Q2 is your 50th percentile. And so this is your 50%. And if I keep going, Q3 is your 75th percentile. your 75%. And technically, your maximum is your 100th percentile, your 100%. See? Now, to better understand what I mean by your 75, your 50, your 25, we gotta work upon the next idea. From your minimum to your Q1, so I'm talking like this here. From your minimum to your Q1, it's 25%. From your Q1 to your Q2, it's another 25%. Ah, so that's why the median I said is your 50%, because from your minimum to your median, it's 50%. It's this one plus this one, right? Okay, so if I keep going with that idea, this box and whisker also has 25% here and 25% here. So what am I trying to say? Your box and whisker, each of these sort of like key points from the minimum to Q1, this is 25%. From Q1 to Q2, this is 25%. From Q2 to Q3, this is 25%. From Q3 to maximum, this is 25%. Okay? So the box and whisker can be very useful to understand, for example, the top 25% of your class, what grades did they get? Okay? That's the sort of thing that it can be good for interpreting. So now that we understand the intuition of the box and whisker diagram, we can go down here and we see that the first one, the first statement says, the data for class A is normally distributed. Now you guys are probably thinking, okay, what the heck? A normal distribution, how does it look like? A normal distribution looks a little bit like a bell. It's also called the bell curve, okay? So the normal distribution looks like this. Now the normal distribution, something that is associated to it, so this is just something you kind of have to know, right? Is that here in the middle, you have your mean, okay? And right next to it, you have a mean plus one standard deviation. And to the left, you have the mean minus a standard deviation. And how does a normal distribution look like? Well, it looks like a bell curve, but more importantly, here you have 34% of your data, and here you also have 34% of your data. See? And the more standard deviations you go over, the more that can sort of change. In fact, if you put normal distribution here, okay? If we put normal distribution over here, ta-da! Damn, it's taking a while to load. Okay, so see how negative one standard deviation and plus one, you have 34%. And then another one over is a little bit less. So one more over is around 13%. Here's around 13%. All right, point is, a normal distribution has this sort of like spread associated to it, okay? And so here, the data for class A is normally distributed. Well, as you can see, if it were normally distributed, this would be 34%, and this would be 34%, which is not the case, okay? Also because, see how it's a little bit more charged to the right? Okay, that means it's not as symmetrical as the normal distribution, and I think that's your main argument. If class A was way more symmetrical, it could be normally distributed, but because it's not symmetrical, it's not, normally distributed. See? What do I mean by symmetrical? Something that is symmetrical can be your face. Okay, for example, you have your face, then you have your nostrils, right? And so it's perfectly symmetrical. You have one eye on each side, you have one nostril on each side, you have teeth on each side. Okay, that just looks weird now, see? But for example, maybe a parabola, right? So a parabola has an axis of symmetry, and it cuts it right in the middle. And so the distance here to here is the same as this distance. Well, this one's not drawn to scale, so let me explain this symmetry thing one more time. If I draw a parabola that looks way more pretty than the one from just now, if this is x, this is y, and you draw this here, right? If this is your vertex, then yes, this is your axis of symmetry. From here to here, it's the same distance. From here to here, it's the same distance. And that's because it's symmetrical, okay? And so this doesn't look very symmetrical because the distance from here to here is not the same as from here to here. The one on the right side is way longer. not symmetrical, not true. Okay, not true. We're just not gonna mark anything because it's not true. Okay, I'll leave on the side though, not true. All right, the ones that are coming are a little bit easier to interpret. See, here we have a higher percentage of students in class A received a grade less than 70 on the exam than in class B. So we go to 70, we make a line straight up, and we start interpreting. So here, they're telling you that a higher percentage of students in class A received a grade less than 70 on the exam, right? And so here it would be true. Why is it true? Because I mentioned earlier that from each of these key points, from example, the minimum to the Q1 is 25% of your data. From Q1 to Q2 is another 25%. So for class A, you know you have at least 25% plus some percent here. Plus some percent here, right? Instead for class B, you don't even have 25%. You don't even have 25% because you don't even go into the you don't pass Q1. That's what I'm trying to say. So for class 1, you pass Q1. For class B, you do not pass Q1. So class A has a higher percentage. See? And now some of you are probably thinking, but class B, this line is like longer, right? Doesn't that mean that they have more? And I'm going to say, nuh-uh. What this says is that the first 25% has grades that are more spread out. Ah, so here the first 25% is more spread out, and up here the initial 25% is more together. Okay, cool. For example, in class A, the first 25% of class A scored between, I don't know, like 62 and between 62 and 67, the first 25% of class A. But for class B, they scored between, I don't know, 52 and 72. And so you can see how in class A, the initial 25% is very close to each other, between 62 and 67, what's in red, while class B scored between 52 and 72, the first 25%. See? Anyways, that's just a little bit of a blah blah so we understand better how the box and whisker diagram works. And now we can do this third one. So this third one says that more students in class B received a grade greater than 90 on the exam than class A. And so here, well, I'm going to go to 90. I'm going to do a line straight up, and I'm going to start interpreting, right? So right off the bat, they are both from Q3 to the maximum. They are both on Q3 to max, right? Now, what we have a little bit of trouble interpreting, right, is which one has maybe like more students, right? So here we have more students in class B received a grade greater than 90 on the exam than in class A. And I'm sure some of you are inclined to say that because there's a little, very little space here for class A, and there's a lot of space here for class B. And I'd say, yes, you're right that visually it seems that way, but technically for class A, you could have a bunch of guys here and only like, I don't know, one or two there. Okay? While for class B, you could have all these guys pretty evenly spread out. Okay? And so all you can say is that the top 25% scored between 86 and 92. That is all you can say. That the top 25% scored between 86 and 92. You cannot say how many of them were above 90 or how many of them were below 90. So for this third one, you actually don't know for sure. You don't know for sure, and so we're just going to leave it as not true because you're not 100% sure, okay? And last but not least, we're going to have the one that tells us that the interquartile range, ooh, interesting. The interquartile range for class B is less than the interquartile range for class A. So here we just need to calculate interquartile range. That is way more straightforward. on the one hand, you can pull it out from your formula booklet, but I'm also going to talk about a little bit like what it is. See? So immediately in your formula booklet, you have interquartile range. See, there it is. It's quite simply Q3 minus Q1. Now let's talk a little bit about what that is, what it means, etc. Guys, technically in statistics, at least for us, we have range and we have interquartile range. See? Now notice, they both have, of course, the word range in them. Okay? And so what's the difference? The range, okay, the one we might be used to, is max minus min. While the interquartile range is Q3 minus Q1. And so the range, which I'm going to do in, I don't know, red, the range is this minus this. While the interquartile range is, in orange, this minus this. And so you might be thinking, why would you want to do the interquartile range? Well, because here you have 25% and here you have 25%. And so, the interquartile range considers your middle 50%, while the range considers the minimum and the maximum. And especially if you're doing a study that has like outliers, or maybe you care more about the average more than all the extreme scenarios, the interquartile range helps you better interpret how the middle of your data like behaves. Okay, and so yes, you would be maybe vouching for like the average or in a sense like the majority, I guess, in a way, but you wouldn't be considering like the max and the min. It's a think about it this way: it's the max and min of the middle for the interquartile range. Okay. Anyways, so that being said, you gotta identify Q1 and Q3 of each. So for example, Q1 over here is going to be 67, and Q3 over here is going to be 86. On the other hand, we have that the Q1 of this guy, class B, is going to be 72, and the Q3 of this guy is going to be 85. So the IQR of green is 85 minus 72. So IQR is going to be, I really can't math right now. I think that's, I think it's 13, but I just can't math. We all have days like that. Okay, so IQR here is going to be 13, right? And the one in purple is going to be Q3 minus Q1, so 86 minus 67. So IQR of the purple one, or class A, is 19. Wow, my brain is really slow today. It's 19. Maybe it's not as slow as I think. So this is my IQR of class A, and this down here is my IQR of class B. So here we said that the interquartile range for class B is less than the interquartile range of class A. That is true. 13 is less than 19. And so here we would put true. Ladies and gentlemen, that is for part A. Notice how the main thing you really have to do is just understand the box and whisker diagram, what it does, how to read it. That's why I did the initial sort of interpretation over here. See? And remember, all you can know are the proportions of the top 25 or the lower 25, stuff like that. How each guy in here behaves and the scores they got, you have no idea. You cannot get that information, at least not from here. All right. Then they tell us that at the end of the year, Mrs. Whitehouse surveyed a random sample of students from each of her 2 large classes to determine how satisfied they were with her teaching. Each student independently selected a value from 1 to 10, with 10 meaning that they were not satisfied and 10 meaning that they were very satisfied. And her data collected from the student's survey is shown. below. So for example, the first guy and student in class A gave her a 7, the second one gave her a 5, a 3, a 4, a 3, etc. See? Well, for class B, they had more students, right? All right, so this is pretty straightforward so far. Mrs. Whitehouse believes a lot of different things. Now, what are the things she believes? And I don't know why she does this in her free time, but she believes that there was no difference in general satisfaction between the two classes. And so she decides to do a t-test because Mrs. Whitehouse has a lot of time. And so she assumes that the data is drawn from a population that can be modeled by a normal distribution and proposes to conduct a t-test. Guys, this whole thing here, you don't really care about too much. The only part you might care about, okay, just to like better identify the buzzwords, the only buzzwords you should really care about is that here it says drawn from a population, here it says t-test, here you have 5% significance level, okay? And the other big sort of buzzword that we have to consider is what she believes, what she's going for, what she's trying. This has to do with the null and alternative, which is for part B, all right? So for part B, you need to write down the null and alternative hypotheses for her test. Now, there is sort of a rule you can follow, all right? And especially for the level of IBAISL, I think you should follow it. The hardcore definition of null hypotheses, and this is agreed like all around, okay? So the null hypothesis is basically a scenario of no change / no difference. And of course, for H1, or sorry, for the alternative hypothesis, it's a scenario of change or difference. How do you express each? Technically, the null hypothesis is the H0, and the alternative is the H1, okay? So just so you know, H1 makes reference to alternative hypotheses, H0 makes reference to null. And so Mrs. Whitehouse believes that there was no difference in general satisfaction between the two classes. Now, how is she evaluating satisfaction? She is evaluating satisfaction by doing this survey. By doing this survey of people grading from 1 to 10. And so technically, if there is no difference between class A and class B, so in other words, it's not that class A is more satisfied or that class B is more satisfied. She's saying, nah, the classes don't matter. They're both just as satisfied with me. Then that means that the averages of each would be the same. So the average of class A would be the same as the average of class B. And this is something that we can figure out that we know she's talking about averages because here it says t-test. A t-test is particularly good for comparing averages. It's particularly good for comparing averages. And so if we're comparing averages, well, my null, my hypotheses have to be associated to that. And so HO, a scenario of no change or difference, means that the average of my first class gotta be the same as the average of my second class. And for H1, they're not saying that class A is more happy because it was in the morning, or class B was more happy because it was in the afternoon, or whatever. They're not saying anything like that. So you're not going to be having that, I don't know, the average of A is going to be bigger than B because they're not saying one of them is better than the other. See? So here, technically H1, a scenario of change or difference. Of change or difference is either this or this, right? So it's either UA being bigger than UB or UB being bigger than UA. And the more mathematical way to express it is quite simply that UA does not equal UB. Will you look at that? So HO has equals, H1 has not equals. Interesting. This is how it usually is for a t-test, for the IB at least, okay? I'm not going to give you a rule of thumb, but I do need you to understand that null is no change and alternative is change. They never mentioned that one class was better than the other, so you're just going to put it as this, okay? Maybe in another scenario they would give you a direction and you would say, okay, maybe the alternative is that the class B is better off, see? But they never mention any sort of priority to one or the other class, so this symbol here is good enough. It's usually the one you end up using. That is for part B. For part C, we need to find the p-value for her test. And so for finding the p-value for her test, you pretty much have to use the graphing calculator. Now it's important to understand when and where to use it. See? And so I'm not gonna jump straight into what you have to do. I'm gonna try to be a little bit more realistic and like be in your shoes. See? So if I were in your shoes and I were doing this test, I would know I have to use the graphing calculator because the p-value, you know you get it from there. But maybe you have no idea like where to do it, what to do first, etc. However, after thinking for a bit and freaking out for only 30 seconds, you're gonna see, here it says t-test. And so you're gonna go to your calculator, you're gonna press stat, and you're gonna search for t-test. Now, it's not in calc, because it's not a test, it's in your test tab. So your test tab, here's t-test, right? So you might end up pressing the first one, and you'll see, okay, it's asking for a bunch of stuff. It's asking for a list. So if it's asking for a list, I need to put in data for my list. So you go to stat, you go to edit, and you dedicate yourself to filling the lists. But wait a second, I have two lists. Here I have list 1, here I have list 2. And what I pressed, which was just t-test, is only one list. And I don't have a frequency list, and this is not a frequency list, the second one. So what is going on? And then you remember, this guy on YouTube, right, he showed me that if you're confused and you're trying to check which one you have to do, first identify, okay, we're talking about t-test, so it's either this second one or this fourth one, which says to sample. And so in the to sample one, bada bim, bada boom, you got L1 and you got L2. All right? And there's a bunch of stuff we're going to do down here, but we'll figure it out in just a moment. See? Initially, you either choose between data or stats. I don't think I've ever seen someone use stats here. Technically, you're plugging in like the mean, the n, the variance like by hand. You can just press data and it calculates it for you. See? But for calculating it for you, you need to find L1, you need to find L2. And so I already named L1 my class 1, L2 my class, L1 my class A, L2 my class B. So I'm going to go to stat, I'm going to go to edit, and L1 is going to be that whole set of values. So to clear my list real quick, I can scroll up, I can press clear, I can press enter, and I can say the 7, the 5, the 3, the 4, the 3, the 8, the 6, the 5. I double check real quick because, I got a minute, so looks good to me. And for L2, for L2, I can again erase this whole thing by pressing clear and enter up top and write down the values for class B. All right. 10, 9, 8, and 3. Yes, we have more values for list 2 than for list 1, but that's okay. As long as you follow and trust the process, everything will be fine. Okay? So now I go back to the test thing. I go to to sample t-test, which makes sense because you have two classes, so it's two samples, right? So here it's asking for a frequency. There is no frequency list. There's nothing like that. Usually you're just going to leave this as 1 and 1. See? Whoops. Why is it showing up like that? Okay, 1 and 1. Awesome. And then you have to choose this U thing, and then you have to choose pooled, right? And then you calculate or draw it. We're going to only be calculating, see? Now, what do you do on this step? So this step technically is your H1. Okay, on this step, you are like sort of plugging in your H1. And as I said, in some scenarios, they tell you like, oh, and Mrs. Whitehouse believes that class B is more satisfied because she would always bring coffee in the morning, right? And so then maybe you would be considering something like this, okay? Or maybe they tell you, oh, Mrs. Whitehouse believes that. This is why it's important. Like whatever your person is looking or searching for has a lot to do with how your hypothesis is going to be. So imagine it's like Mrs. Whitehouse believes that the afternoon class is more satisfied because they're closer to like leaving school. Then okay, you would do this one. See, but that would change your H1. Okay, so in this case, we identified that H1 is that your first mean does not equal your second mean. So that's why it's going to be this first option. Also notice, remember how we said that t-test is particularly good for comparing averages? The symbol for average is this guy. And here you have only averages because you're talking about a t-test. Oh, it all comes together now. For pooled, the intuition is the following. For pooled, if your two samples have the same variance, you're going to leave it as pooled. Okay, that's like the hardcore math definition. What I want you to have the intuition for is that if they come from the same group, it's going to be pooled. And so here it says that she assumes that the data is drawn from a population. And so they're drawn from a population from the same population, so it's going to be pooled. If it's two different populations, you would say not pooled, okay? And last but not least, I don't think I've ever seen a scenario, at least in the IB AISL, where you put that it's not pooled, okay? So rule of thumb, if you're unsure, leave it as yes pooled. I am yet to see an example where you have to put no pooled. Dead ass, I'm just being honest, okay? But the argument for leaving it pooled is this line here, okay? They both come from the same population, so it's pooled. If they came from different populations or different places or whatever, then it would be different variance. It would probably be unpooled. All right, enough blah blah. You go ahead and calculate. See, you calculate, and a bunch of stuff gets thrown at you. So you got your t value, you got your p value, you got the f, and you got the mean of each. See, the mean of each, the variance of each, blah 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 blah. Okay, I mean standard deviation of each. So what do you do from here? Well, part B is just writing down the p value. See, I mean, sorry, part C is just writing down the p value, which is right there. It's p equals 0.0952085. I got good memory, see? And so here, for significant figures, right, you count 1, 2, 3 from this one, okay? Because in significant figures, you only count after your first number that's not 0. Okay, so these two you will not consider as significant values. From 9 onwards you do. So the 2, do you round it up or keep it the same? You keep it the same, so P is going to be 0.0952. All right? All right. That is part C, easy 2 points. For part D, you need to write down the conclusion of the test and give a reason for your answer. For concluding these tests, there's a couple different ways. It all depends on what they give you, okay? Sometimes they give you a significance level and a p-value, and you just compare those two. Other times, they give you a critical value, and they give you and you discover your t-value, and you gotta compare those, all right? And so for this exercise, basically what I want you to understand is that you compare p-value with significance level, okay? In other cases, you gotta compare like the t-value with, I think it was critical level, okay? What's intuition? The t-value in the critical level, as you can see over here, the t-value is like 1 point something, right? It's like a bigger number. It's not a percent. And so you either this is the thing, you either compare percents or compare like real numbers, okay? In this case, p and significance level is a percent, and so you're going to be comparing the p value to the significance level. Significance level. And so which one is bigger? Well, 0.0952 versus significance level, which is 5%. How do you express percent as a decimal? You just divide it by 100. And so you take this 5, you divide it by 100, you end up with 0.05. So which one is bigger, you guys? The p-value is bigger. And so the conclusion here is that there is, think about it this way, because p-value greater than significance level, there is insufficient evidence to reject HO. The other way you can understand this is that if there is insufficient evidence to reject HO, then you accept HO or you retain HO. So you weren't able to reject HO, so you gotta keep it. And so if you keep HO in this case, you would basically say, okay, yeah, Mrs. Whitehouse's belief is correct. There is a scenario of no change. There is no difference in the general satisfaction. All right. But yeah, that is how you would conclude this sort of exercise. And so I know it might be a little bit weird, like, okay, why does this work how it works? Why does this mean you reject? I can get into it. I can try to explain it intuitively. But this is one of the few things I'm going to tell you. You're better off just memorizing this, okay? If you ever have a p-value that's greater than significance, reject. I don't suggest memorizing stuff, but most of this stuff you don't have to memorize. Most of this stuff is in your formula booklet. So one of the few things I would ask for you to memorize is how to conclude these tests, okay? And worst case scenario, maybe you forget how to conclude it, but you did everything else. See? Usually the conclusion is the last part. It's worth 1 or 2 points, usually 2. 1 point for doing this step here, and another point for saying it correctly. See? So even if you don't remember well how to conclude it, just writing this would already give you an answer. I mean, a point. This would already give you a point. All right? And then concluding correctly, it's literally worth 1 point. See? So might as well memorize it. It's worth 1 point. I wouldn't dedicate a lot of time to something that gives you just 1 point. So knowing how to conclude this gives you 1 point. Getting the p-value and all that stuff gives you a little more. See? So knowing how to get the p-value gave you 2. And technically, it gave you 1 more because of this step here. See? And I'm not even kidding. Guys, look at the mark scheme. For part C, you get 2 points for just getting the p-value. And for part D, you get 1 point for comparing the p-value to the percent that they gave you. And you get only 1 other point for knowing how to conclude. See? So I suggest memorize how to conclude. If p-value is greater than significance level, reject your HO. Sorry, fuck, I said it incorrectly. If your p-value is greater than your significance level, which is what we're looking at here, there is insufficient evidence to reject. So you don't reject, okay? All right, you guys. Sorry about that mess up at the end, but it goes to show it can get confusing, so might as well memorize it, okay? That's the best way to go. Ladies and gentlemen, that is for number 9. All right, guys, number 10, we have that Rita is playing a game, and in the game, she must roll a fair 6-sided die. Okay, a fair 6-sided die. If she gets a 5 or a 6, then she wins a prize. If not, she has another chance, but this time she must flip a fair coin. If it lands heads, she wins a prize. Alright, so it's very important that we understand that first, it's the die, where it's a 5 or a 6 to win, and later on, it is a coin. And in this coin, if it's heads, she wins. Okay? So that is the key information we have to consider. And for part A, we need to complete the tree diagram by writing in the 3 missing probabilities. Now, notice how in this tree diagram, we're very used to having something that looks like this, right? And in this case, we have just this. The reason for this is because we only go as far as winning. The moment she wins, she does not need to throw the coin. Alright, so first thing first, that's why this tree diagram looks a little bit weird. On this version of winning, we don't care about throwing the coin anymore because, well, she already won. Okay, cool. The second thing we have to consider is that for tree diagrams, the probability, okay, of each of these little sort of like sticks is gonna equal 1. Okay, so this plus this equals 1. This plus this equals 1. And this plus this equals 1. Why is this useful to know? Because now, for example, if this is 1/2, then this is also 1/2. Why? Because 1/2 plus 1/2 equals 1. Why does it need to equal 1? Because 1 as a percent is 100%. And in probabilities, technically, you consider all scenarios. And so here, like this 2 blue circles is all scenario. The scenario of winning and not winning has to equal to 1, has to equal to 100%. So 1/2 plus 1/2 gives you 2/2, which is 1. There's your 100%. Okay, so again, for tree diagrams, each of these sort of sections has to add up to 1. So over here, I can put this 1/2, perfectly legal. And now we need to fill in the information for the die. So the die that I have in green, let's recall that she says that if she gets a 5 or a 6, she wins a prize. So what is the probability of rolling a 5 or a 6? Well, a dice has 6 sides. 1, 2, 3, 4, 5, 6. And each side has number 1, number 2, number 3, number 4, number 5, number 6. So think about it this way. From 1 through 4, she loses. So here, lose, 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 lose. And here is win and win. What's the probability she wins? Well, it is 2 over my total. So it's going to be 2 over 6. You can think about it this way. It's 5 or 6 divided by your total. So 2 over 6 is the same as 1 over 3. So that was a little bit of a more, perhaps like longer explanation. But the point is, for winning in the die, it's going to be 1 over 3. And so for winning is 1 over 3. For no win, it's going to be 2 over 3. Because that is what adds up to 1. For some of you, it might be more intuitive to leave it like with the total amount. So if you want, you can leave it as winning is 2 over 6 and no win is 4 over 6. Both of them work. You don't have to simplify the fraction. The IB doesn't care about simplifying the fraction. Okay? I'm going to leave it simplified because later on it's just easier to do the math. Okay? So win is 1 over 3, no win is 2 over 3. So that is for part A. For part B, we need to find the probability that Rita does not win a prize. And so in probability, it's very, very important that we always consider the different scenarios. So the obvious question is, which is the scenario, or which are the scenarios where Rita does not win a prize? And so it's very important that we consider the whole tree diagram. So in this case, what a lot of people would commit as a mistake is say, okay, probably no win, 2 over 3. And they think they're done, right? And I would say, So first, it's no win on dice, but then it's no win on coin. So it would be 2 over 3 times 1/2. In other words, 2 over 6 or 1/3. So that is a probability of not winning a prize. Now I'm sure there's at least one of you thinking, dude, I just never understood why you multiply probabilities and when do you add them? What the heck is going on? Guys, when you multiply, it is because you're thinking in the word and. And if you add, you're thinking in the word or. So think about it this way. If I think in terms of and or, okay, it's very important. Think in terms of and with or, okay? So if you think in terms of and or, the probability that, or the scenario where Rita does not win a prize, the scenario where she doesn't win a prize is no win die and no win coin. So what's the probability of no win die? 2/3. And gives you the multiply, and no win coin is 1/2. So 2 over 3 times 1/2. 2 over 6, 1 over 3. Same thing I did up there. See? So that is one way to think about it. If you think in terms of and or, and is multiply, that is going to put 2/3 times 1/2. Okay? The other way you can think about it is that in a tree diagram, if you want to reach like the coin no win, you have to go through die no win. So you have to do 2/3 times 1/2. Okay? The only sort of place where you would be adding is if you consider, I don't know, the probability of no win and the probability of no win die and no win coin, and maybe this line here. See? Then you might be adding this one, like this whole line, with this whole line. But for this example, we don't face that. If you want to find an example like that, I'm sure there's one on my channel. Just look up tree diagram for the buzzword and you'll find it. Anyways, whatever. For part B, it's 1/3. Okay? This 1/3 here, or this 1/3 there. Same idea. Then for part C, it's a little bit more weird because there's a buzzword, given. And so given is an important buzzword that needs to immediately tell us that we are thinking of conditional probability. Okay? And so given that Rita won a prize, find the probability that she got a 5 or 6 when she rolled the die. And so of course this one is way harder. See? And it's very important we understand how to think about given probability. So let me show it super visually for now. Imagine you have a Venn diagram, okay, where you have A and B here, A and B. So I'm gonna do another Venn diagram right away. Okay, the same scenario, A, B. If I am looking for the probability of A and B, what is your total? Your total is this whole thing. So this is where you're drawing from, okay? This is your whole total, and this is A and B. Okay? For probability of A given B, okay, this little stick here is for given. For probability of A given B, it's because you are drawing from B. So because you are drawing from B, what is the probability that you get A? And so notice what happens in given probability. In given probability, where you draw from decreases or changes. And for us, it's always going to be decrease, okay? So in other words, your denominator decreases, okay? And strictly speaking, there is a formula for this. If you go to conditional probability in your formula booklet, there it is. So probability of A given B, remember this is A given B, you have A and B divided by B, okay? So the second one goes on the denominator, okay? You can use the formula for this and it would work, and maybe I will do it that way, I'm not sure. But you can also think about it as just your denominator changing. You have to change from where you, like your total, see? And so in this case, actually, what is your given? You have given that Rita won a prize. And so technically here, your B is that she won a prize. Okay, so winning a prize, if she won a prize, what's the probability she rolled 5 or 6? So technically, just so that we understand very well what's going on, my new universe is only when she wins. And so your new universe is like you're drawing from this and from this. Okay, so that is your universe now. It's only the scenarios where she wins. All right? And so where she wins, what's the probability she got a 5 or a 6? So if she gets a 5 or a 6, she straight up wins, right? But your new sort of set of scenarios is the 2/3 and the 1/2, right? And so a way you can think about it, and I think it's more friendly if we actually use the equation for this one, you can think about it this way. So the equation is that probability of A given B equals probability of A and B divided by the second one, probability of B. So again, this little stick is given, right? So given that read I want a price, that means that B is going to be my given. So you can have that, well, your A is going to be everything else. So your A is going to be getting up 5 or 6, right? Now getting up 5 or 6 on the die is winning on the die. All right, whatever. So 5 or 6 on die, given, win. So that means you have the probability of 5 or 6 die and win divided by probability of win. Okay? Now, the one on top, 5 or 6 die and win, is just this part here. Probability of die and win is 1/3. So you have 1/3 divided by the probability that you win. Now there's two scenarios for winning, right? You have the scenario that is up here, that is the 1/3, or, so it's plus. So you have the scenario where it's win by die, or lose die, win coin. Okay, I'm going to write that down because it's very important. So you have two scenarios for winning. You either have win, think about it this way. Scenario 1 is win die. Scenario 2 is lose die and win coin. So the two scenarios for, so these are the two scenarios for winning, right? So if I go ahead and say, okay, scenarios for win, or better said, so if you, how do I say it? So if you combine the two scenarios, the cases where you win are scenario 1 or scenario 2. And so scenario 1 or scenario 2, what was or? Or was plus. It was add. So scenario 1 or scenario 2 means you're going to end up with win die or lose die and win coin. See? So here's an and, right? In other words, win die is 1/3, because it's the one up here, right? This 1/3. Or, it's going to give you the plus. Lose die, so lose die is 2/3. So lose die. And, so it's times win coin. Win coin, 1/2. So this is for finding the two scenarios for winning. See? And we did say that the denominator is probability for win. Oops, my bad. The one on the bottom is probability for win. So that means I have the 1/3 plus this. Okay? I mean, it's that whole thing. So it's 1/3 plus 2/3 times 1/2. All right? So that means if I combine the stuff on the bottom, I end up with 1/3 plus 2 divided by 6, right? And from here, I mean, you can just work around with fractions and stuff, but you can also just plug it all into your calculator and forget about it. So in your calculator, you can do alpha y equals, it brings up a fraction. And I need to have fractions on top and on the bottom. So I can do it again. Down here, I can do it again. So up top, we're going to have the 1 and the 3. On the bottom, we're going to have the 1 and the 3 plus another fraction, the 2 and the 6. So all of this is going to give you 1/2. So all of this, the probability of 5 or 6 on die, given that you're winning, is 1/2. All right? So that is for part C. Sometimes it's good to think about it from the visual aspect, like the Venn diagrams that I drew, and making your denominator smaller, but you can always just stick to the formula. In this case, for me, thinking about it as the Venn diagram was a little bit harder, so I stuck to the formula. As long as you're rigorous, and remember that the second one goes in the denominator, you'll be fine. What do I mean by this? Notice how here the B goes on the bottom, okay? And remember that this stick is A given B. So, in this case, the given, they said it at the beginning. So this is your B, and everything else is your A, okay? So careful with that. The B is whatever is after the word given, okay? It's not always going to be given in a logical order. Sometimes they're going to first say given, so they're first giving you B. All right, careful with that. So remember, this is a little stick, means given. So given B is a way to find it, okay? Anyways, enough blah blah. That is for part C. Notice how it's worth 3 points. You gotta know given probability, okay? It's a little bit harder, but it's a lot of points for just understanding it a little bit better. And knowing how to do a tree diagram gives you 2 whole points. It's not a bad deal, is it? All right, guys. That is for number 10. All right, you guys, here for number 11, we have that Nicole, okay, works at a local school 5 days each week. Nice. She drives an old car that has a 72% probability of starting? Dude, I don't know if I would use a car like that, but whatever. Nicole's Nicole, everyone does their own thing. The probability of the car starting on a given morning is independent of it starting on any other morning. So what it is saying here, all right, probability of the car starting is independent of it starting on any other morning, is that if, for example, yesterday it did start, that doesn't mean that today it's more likely for it to start. Or if yesterday it didn't start, that doesn't mean that today it's more likely for it to not start. Okay? So it doesn't matter what happened yesterday, the probability will always be 72%. All right? So for part A, we need to find the probability that Nicole's car starts on exactly 3, so this is important information, in a particular 5-day work week. And so from here, I mean, I can just jump and show you what to do on the calculator right away, but I think it's important that we talk a little bit about your approach, how you think about the problem, etc. So some of you are probably thinking, okay, so there's a 72% probability of it starting. So 72% of start. That does not look like 72. So there's a 72% of start. So that means you have, 1 minus 0.72. That means I have a 0.28 of not start, right? And so 72% is the same as 0.72, right? And so from here, maybe some of you would think, okay, technically I can do a tree diagram, right? So this is start, this is not start. And up here, I'm going to have 0.72. And down here, I'm going to have 0.28, right? And you can do this for the 5 days. But you're going to notice that, okay, this is first day, this is second, this is third, this is fourth, this is fifth. Your tree diagram ends up being huge because you have to add this, 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 this. You have to add so many different things to this tree diagram that you end up with a lot of different probabilities. And calculating this is going to be a headache. It is going to be annoying, and there's definitely a faster way. But why am I pointing this out? I'm pointing this out because if you're thinking in a tree diagram, then what is behind the scenes is that you're thinking of A or B. What do I mean by this? It is heads or tails. It is only 2 options. So if you're thinking of only 2 options, which is a little bit like the tree diagram, right? It's either start or no start, start or no start. If you're thinking of only 2 options, then, well, only 2 has a root associated to it, right? Only 2 has bi associated to it. You have bisexual, you have by this, you have by that. And so technically here, this guy's going to talk about binomials. This guy's going to talk about binomial distribution, all right? So point is, if you ever find yourself thinking of only 2 options, start or no start, rain or no rain, heads or tails, anything like that, okay? Go to them all or not go to them all, yeah, it's a binomial distribution, okay? And so I want to talk about this because it's the first step to realizing, I need to use the binomial distribution stuff on my calculator. Now, what does your calculator have? So because it's a distribution, you gotta hit that blue button here on top of vars. So you go to second, vars, and here are your distributions. Now, we're very used to using the normal distribution, right? And so the binomial one is way more down, which is here for letters A and B. Now you only have two tools, so that's good news. There's not too much we have to learn, right? And so here's the intuition I'm going to share with you. Binomial PDF versus binomial CDF. For PDF, it's just that amount. And for CDF, it's going to be from 0 to that amount. Okay? It'll make a little bit more sense in just a second. See? So binomial PDF is just that amount. Binomial CDF is from 0 to that amount. And so because PDF is just that amount, and here they ask for exactly 3 mornings, all right, I gotta use binomial PDF. So this is the first thing we can kind of identify. PDF is for an exact amount, right? So maybe I'm gonna write exact, and CDF is from 0 to that amount. So maybe you're thinking of at least, stuff like that. Okay. All right. So as long as you associate PDF to an exact amount or just that amount, you'll be fine. Now, so at this point, you're probably taking the test. You identified its binomial PDF. You're looking at exactly 3. So you're going to open up your calculator and press binomial PDF. And from here, oops, I gave away a little bit what we have to put. My bad. But point is, from here, you're going to see, okay, it has trials, it has p-value, it has x-value. There's definitely a couple things we have to fill in. What is what, right? So trials, think about it this. Trials is sort of like the amount of times you're going to be throwing the coin, okay? Trials is the amount of times you're throwing the coin. P is the probability that, the head lands heads. I mean, sorry, the coin lands heads, okay? Or in this case, it's going to be the probability of it starting, right? And then the x value is how many times you want it to successfully have started. All right, so let me explain that one more time because it's super important. So for part A, we're going to be using binomial PDF because we have exactly 3 mornings. Okay? And so from here, we need to fill in trials, we need to fill in a p-value, and we fill in an x-value. Okay? So for trials, it's actually, let's start from below. I think from below makes a little more sense. So your x value is how many times you want your event to happen. Okay? So if it's at exactly 3 mornings, then exactly 3 times I need my car to start. Now, this P is the probability of it starting, right? Why are we looking for the probability of it starting? Because here it says, find the probability that Nicole's car starts, okay? So probability of it starting, we said earlier 72%. So that is why this P, which is just probability, okay? So this P is going to be 0.72 because 0.72 is 72%, all right? And now for trials, think about it this way. It's, okay, you want it to start 3 times out of how many days? So 5 days because it's a 5-day work week, right? And so trials will be 5 because there's 5 days in a work week. The probability of it happening is 72%, and you want to happen exactly 3 times. So you put an x value of 3. So you put all of this into your calculator. So trials 5 because it's a 5-day work week, 0.72 for probability of it starting, x value of 3. It happens exactly 3 times. Exactly, so we're using PDF. You paste. Enter, enter, there it is. So the probability for part A is going to be 0.292626. All right? Yes, and if you consider significant figures, you would count 1, 2, 3. Do you round it up or keep it the same? You round it up. So significant figures, you can leave it as 2.93. If you want, you can always leave your answer with the long form. I suggest doing the long form. Just forget about sig figs. Anyways, how would you show your work? You might be asking. You need to show evidence that you used the binomial distribution. And so technically, see how your calculator here, there's like this line up there. Okay, so this is evidence that you did what you did. Okay, so for your method point, you can literally write binomial PDF and that whole thing in parentheses. 5, 0.72, and 3. And so what this is saying, like just so we really understand, what this is saying is that you went to your calculator, you used the binomial PDF function, and for the first thing they asked, you put 5. For the second thing they asked, you put 0.72. And for the third thing they asked, you put 3, which is exactly what we wrote over here. Okay, so this is this. All right? So right now, you would get one method point over there and one answer over here. Okay? I know the thing of writing out the binomial PDF might seem a little bit ridiculous or tedious, but it does give you a method point, so do it. If you want to get really, 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 really fancy, you could express it like this, all right? Which is like the more hardcore mathy way. But for me, more intuitively, we used our calculator. Our calculator spit this out, and if you write that, it'll give you the method point. As long as there's evidence of using the binomial distribution, it's fine, all right? Anyways, that is for part A, okay? Part B gets a little bit more exciting because we have the Nicole apparently walks to work on mornings when her car does not start and it's not raining. On the other hand, Nicole takes the bus to work on mornings when her car again does not start and it is raining. And so what's the difference? If it rains, if it rains, she takes bus. If it doesn't rain, she walks. That simple. Not rain walk, rain bus. If her car doesn't start. If her car does start, she takes her car. Why would you not, right? So, then they tell us, in respects to rain, that where Nicole lives, there is a 42% probability of rain on any given morning, independent of any other morning. Whoops. Independent of any other morning. Now, we already talked about independent of any other morning. It means that if it rained yesterday, that does not change the probability of it raining today. If it did not rain yesterday, it does not change the probability of it raining today. Independent. This 42% is not going to change. Every day it'll be 42%. The probability of Nicole's car starting is independent of the water. So it doesn't matter if it rains or not. Nicole's car probability of it starting does not change either. All right, this is a pretty standard assumption. Probabilities are not going to change. Now, for part B, this is where it gets juicy. We have find the probability that Nicole will not have to take the bus in a particular work week. And so now we have to start thinking, okay, what are the scenarios where she does take the bus? What are the scenarios where she doesn't take the bus? What are the scenarios where she takes the car? What are the scenarios where she doesn't take the car? And from here, actually a tree diagram helps. So we talked a little bit about how a tree diagram helps a lot for like one thing happening or the other thing not happening, right? And so I filled it up with car starting, not starting, car starting, not starting. But you can also use a tree diagram for two independent events, okay? For example, you can also do a tree diagram for like, I don't know, heads or tails, and then whatever, like even number on a dice, okay? Or odd number on dice, okay? And so, yes, here you have a coin and here you have a dice. That's fine, okay? You can have that on your tree diagram, okay? That's legal. You can do it, and there are exercises on the B that have stuff like that, okay? Point is, I'm going to draw a tree diagram to better understand one day. So this is going to be just for one day, right? I'm not going to do the 5-day work week because it would be a crazy tree diagram, okay? A 5-day work week would be an insane tree diagram that we want to avoid. But this can help you find probabilities for one day, all right? So a tree diagram for one day would look something like this. For our good old friend Nicole, we have either the car start or the car no start, okay? So the car starts or no starts, right? So if the car starts, she's gonna go on car, and the probability of this is 72%. So here I'm gonna put 72%. And no start means no car, which is 28%. All right, so if her car starts, she's just gonna go on the car. So your tree diagram is gonna reach there. See, you don't care from here if it rains or not, because she's going on her car. So whatever, right? Now, if it doesn't start, if it doesn't start, there's a difference between walking if it doesn't rain and bus if it does rain. Okay, so from here I'm gonna put rain, which we know is 42% probability. So if it's no start, then it's rain, which is this here. Oh, sorry, no start and rain. So no start and rain is this, right? No start and rain, bus. So no start and rain, bus. What's the probability of this? 42% probability of rain, right? 42% probability for rain, right? Notice how here the 42% is associated to rain, okay? And for example, this 72% is associated to start, okay? The probability of taking the bus has to do with this scenario here. It's like taking that path. And so it's not that the probability of bus is 42%, it's that the probability of rain is 42%, okay? I'm going to talk in a moment now how to get probability of going on bus, not going on bus, stuff like that, see? Just thought I'd point that out for a second. Don't get lost in the sauce. 42% is probability of rain. Okay, we have not yet found probability of taking the bus. And so we have rain or no rain. Rain, no rain. And the probability of no rain is 58%. Because if the probability of rain is 42, right? That means I can do 1 minus 0.42. This gives me 0.58. So probability of no rain is going to be 58%. So if it's no start, so no car, and no rain, no start, no rain, walks. So here I'm going to put walks. All right? All right. And so from here, for one day, I can try to calculate the probability that Nicole will not have to take the bus to work, right? Now, this is very important that you think about probability the right way. So right now, you're trying to find the probability that Nicole will not have to take the bus. So probability not have to take bus. For finding the probability of not having to take the bus, you first think of the scenarios where Nicole doesn't have to take the bus. And so what are the scenarios where Nicole doesn't have to take the bus just looking at this tree diagram? All right, take a moment, try to find them. What are the scenarios and how many where Nicole doesn't have to take the bus? Here we have two scenarios. You have this first one where the car starts and so she just goes, no bus, right? And you have a second scenario where it's, okay, your car doesn't start, but it doesn't rain, so she walks. Those are your two scenarios, okay? And so from here, I'm going to have scenario, green and scenario dark green. So I have scenario light green and scenario dark green. And from here, you gotta find the probability of both, right? So what's the probability of light green? Well, quite simply, it's just 0.72. So there, the car starts right away. It's 0.72. Yes, it's that simple. The scenario of dark green is a little bit different because to reach no walk, that means you pass through no rain and pass through no start. And so think about it this way. So scenario 1 is just car start. So car start is 0.72, right? scenario 2, or dark green, is Carnot start, and that was a crazy voice crack, and no rain. Okay, so notice how suddenly I put the word and in here. And in probability, you guys, and whenever you find yourself saying and, you're gonna be multiplying. And whenever you find yourself saying or, you're gonna be adding. Yes, it is that straightforward. So this, notice how a lot about what I'm talking about here is how to think about probability. The numbers and the fractions you're putting into your calculator are really not that hard, but you do have to keep in mind, if you're thinking in terms of or, it's plus. If you're thinking in terms of and, it's multiply. If you're thinking in terms of one or the other, it's binomial. Okay, that kind of stuff is what we need to identify. So scenario 2 is car no start and no rain. And so from here, because and is multiplied, probability of car no start is 0.28, right? It's this 0.28 that's here, times, because we have and, times for and, probability of walking, right? Probability of rain, 0.58, right? And so no start, 0.28, and means I multiply, no rain, 0.58. That is how I ended up with this, okay? And last but not least, the scenarios where Nicole doesn't have to take the bus is what we have in light green, and we have what we have in dark green, so 0.28 times 0.58. But now, the probability of not having to take the bus are the scenarios where Nicole doesn't have to take the bus. And the scenarios where Nicole doesn't have to take the bus is scenario light green or scenario dark green. Oh wow, will you look at that? So now we put in an or, and what was or? Or was add. So from here, or your last line of math, right, for one day, you will have 0.72, which is your first scenario, or these voice cracks are on a roll today. So 0.72 for your first scenario, or 0.28 times 0.58 for your second scenario, okay? And so you put all of that into your calculator and you find 0.72 plus 0.28 times 0.58. So this gives you 0.8824. 0.8824. Now we really need to understand something from here, okay? What did we just find? We just found the probability of not have to take the bus on one day. Okay, this tree diagram is just for one day. And this problem is worth 4 points. So it can't be that simple. Okay? Here they tell us to find the probability that Nicole will not have to take the bus in a particular work week. Okay? So we just found the probability of just one day, and now we need to sort of like extend that to the whole work week. So the probability of not one day, right? The probability of not having to take the bus in a whole particular work week means that we have Monday, no bus, and Tuesday, no bus, and Wednesday, no bus, and Thursday, no bus, and Friday, no bus. So you have a bunch of ands. You have Monday no bus, and Tuesday no bus, and Wednesday no bus, and Thursday no bus, and Friday no bus. And so from here you realize, okay, probability of Monday no bus, 0.8824, times Tuesday no bus, 0.8824, and Wednesday no bus times 0.8824, and so on and so forth. So what you end up with is 0.8824 times 0.8824 times 0.8824, and all of this will be happening 5 times. Why 5 times? Because we're talking about 5 days. Okay, so you can open up your calculator. You can put 0.8824 0.8824, put it to the power of 5, and boom, this is Nicole not taking the bus 5 times. So probability that Nicole doesn't take the bus 5 times. Boom, there it is. So probability of Nicole not taking bus is 0. For part B, we end up with 0.53496. 3496. If you want to do significant figures, you can count 1, 2, 3. So you round it up, I'll give you the same. You round it up, so 0.535. All right, guys, this is one way to do it. It's what I think is most intuitive, especially because of this step here. And again, always try to think in and or ors, okay? The hardest part of statistics and probability is how you approach the problem, how you think about the problem, see? So I hope that thinking about one day and then taking it to a whole week helped, okay? Now, if you want to stick to the calculator using the binomial distribution and all that stuff, okay, technically from here, from the 0.8824, you can take it to your binomial PDF or CDF over here. See? Now notice, because we're talking about the probability that Nicole will not have to take the bus, okay, that means she exactly of the 5 days of the week doesn't take the bus. So notice that exactly 5 times doesn't take bus. So exactly 5 times she doesn't take the bus. So you can go to the PDF once again, 5 trials, because we're talking about a whole work week, right? Our probability of not taking the bus is 0.8824, and our x value, which is the amount of times we want this to happen. So we want Nicole to not take the bus 5 times. Our x value is 5. Yes, trials is 5, x value is 5. 5-day work week, Nicole doesn't take the bus 5 times. Exactly 5 times. Boom, it's the same number, okay? So now maybe you also learned a little bit what your calculator does behind the scenes, all right? This is, to my liking, the most intuitive way to approach this problem, okay? I know there's another approach, which is instead of doing the light green scenario and the dark green scenario, you just find the probability of this, okay? And so you do everything thinking like not, right? So you would do 1 minus what you get there, and then you put that into the calculator and stuff like that, see? For me, it's more intuitive if I talk about the two scenarios, the light green, the dark green. But I'm just saying, once you look at the answer key, you're gonna see that there's more than one way to do this. See? So this right here is what I told you guys, right? So here you're finding the probability of taking the bus, right? There you have the probability of taking the bus, and you work backwards from there. That's why it's also 1 minus this. See? In fact, 1 minus that is going to give you the probability of not taking the bus. Okay? So you can work backwards. Maybe it's more intuitive. I'm just pointing it out in case it helps you. Okay? For me, it's way easier if I think about only the scenarios of not taking the bus and work from there. Okay? But, yo, to each their own. All right? I hope it helped. And that is number 11. Alright, you guys, and now for number 12. It's a fairly easy problem with easy points, but there's a lot of key buzzwords that if you don't understand, you're just not going to get it, okay? So context-wise, you got to know this unit well in order to get easy, quick points, alright? So we have our homeboy Thurston. Thirsty Thurston believes that more popular musical artists sell more albums, and so he begins to investigate this belief by randomly selecting 8 musical artists and collecting data on the number of followers each of the artists has on a particular social media platform. Blah blah blah. He then collects data on the number of albums each artist sold in the first week after releasing an album, and his data is shown on table 1. Table 1 is right here. Just so that we understand, for example, the guy, for example, artist 4, with 2,300 social media followers, the number of albums he sells in the first week in thousands is 94.9. The guy with 94,400 social media followers sells around 595.5 albums, thousands of albums in the first week. Okay, so that is information it's giving you. And then Thirsty Thurston, decides to calculate the Spearman's rank correlation coefficient. And for this, we need to complete the table of ranks shown in table 2. Now, this is what I mean by understanding buzzwords. A lot of you probably read this and say, all right, I'm going to the next one. Okay? And you realize that it's number 12. There is no next one, and you've been skipping all the problems and you didn't study enough. Just kidding. I hope that doesn't happen to you. Point is, there's two main buzzwords that you might have read that include the word Spearman. So you have Spearman's product moment correlation coefficient, something like that. I don't recall incredibly well how it is. And the other one that we have right here is Spearman's rank correlation coefficient. Now we need to understand the following. They are both for correlation because they both have the word correlation inside of them, okay? It's just the way in which they calculate correlation is a little bit different. Now, first things first, what is correlation? Correlation helps you find a relationship between two variables. So for example, if you have, I don't know, hours playing League of Legends, and here we have depression. No, just kidding. And we have hours playing League of Legends, and here we have your rank. Okay, the more you play League of Legends, you tend to have a better rank. Okay, and so you might have a bunch of different data points, and you try to find like a line that is like the average of all these points. You're probably gonna end up with a line that looks a little bit like this. Okay, and so this would be correlation, okay? And the R value of this is your correlation, quite literally. An R of 1 is a perfect positive correlation, okay? And an R of negative 1 is a perfect negative correlation. And an R of 0 is basically no correlation, okay? Because an R of 0 is a flat line, no correlation, no direction, right? If you have it equals to -1, well, it's perfect, but it's negative. See? So that would be the more you play League of Legends, lower your rank is, which would be my scenario, okay? Maybe your scenario, because you have quicker reactions, because you're probably a millennial, not a boomer, is going to be this right here, okay? Anyways, enough jokes. Back to the world of math. That is correlation. Okay, you try to find the relationship between two variables. If this one increases, how much is the other one prone to increase? Okay, and so usually, especially for Spearman's product moment correlation coefficient, you have a lot of different points, and you're trying to find the value of R that sort of like cuts between all of these, right? For Spearman's rank correlation coefficient, it is very similar, just that instead of plugging in these values here, so this would be for Spearman's product, for Spearman's rank, you want to make sure that all of these numbers are ranked together, okay? And so I have a couple of videos doing Spearman's product moment correlation coefficient, but basically this would be all 1, this would be all 2. You go to stat line reg, and you're going to get your R value, okay? And for this one, it's actually the same thing. So you can sort of boil it down that the procedure for finding the correlation is always the same. You're going to find, you're going to write down this is L1, list 1, this is L2, list 2, go to stat, go to line reg, and this is going to give you your R value, okay? The thing is, because we're talking about a rank correlation coefficient, you got to rank the social media followers, you got to rank the albums sold in the first week. What do I mean by rank? You have to order them, okay? And so clearly, as you can see here, artist number 8 is number 1. Why would artist number 8 be number 1? Because artist number 8 has the most amount of social media followers. Which one has the next largest amount? This 49,500, which is why the 49,500 is second in rank. Okay, what is third in rank? It would have to be this guy here. Kapow. Fourth in rank, this guy here. Yada, yada, yada. See? So the point is that Spearman's rank correlation coefficient is going to see, okay, here you have first with first, right? But do you have second with second? Do you have third with third? And that is the correlation that they're trying to find. Okay, that is the cool thing about Spearman's rank correlation coefficient. Anyways, enough blah blah. Let's go piece by piece. And so looking at just the table on the bottom, because that's all we really care about, because we're only trying to fill in these guys here, right? So looking at only the table on the bottom, the one that is in first place clearly is this 595. Which one is the next largest after 595? The 123, okay? So we're going to go ahead and start circling so that we make sure we already counted it, okay? So the 123 is going to go here, so that means this one is second in rank, second biggest. Which one's the third one? Probably the 90 something, right? Just going to double check, yes. So the 90 something is the third one, that is artist 4. Here it is. What's the next one in rank? Probably the 60, it's the 60, so here you would put 4, see? And so you keep going from there, keep filling in. Next biggest would be the 52, so artist 5, right? Boom. And then next biggest would be this guy here, so it's going to be 6. Next biggest is this one here, 7. And then 8, see? And so notice how, yes, the artist with the most social media also sold the most, but this guy that also had the most social media was 6th place for selling the most. And so, maybe your R value is not going to be perfect. Maybe it's not going to be equals to 1. A perfect one would be if all these numbers matched, but clearly they don't. For example, this third guy ranked 4 in selling, and this fourth guy ranked 2nd in selling. So, something fishy is going on here. Maybe Thurston isn't completely right. Or actually, well, he's investigating, but his belief that the more popular the music artist is for selling more albums, maybe it's not necessarily true. Okay? And this is just by looking at the data, looking at the rankings. Okay? So that was a little bit of blah blah first to understand why people do this in the first place. But going back to the procedure you're going to memorize because you have your test tomorrow, okay, you put L1, you put L2, you go to stat line reg. Okay, these are your 3 steps. First, line 1, list 2, stat line reg, write down the R value. Okay, so you're going to go to, so you're going to go to the list, right? So to find list, you go to stat, okay, this stat button, and then you go edit, okay? And so from here you have list 1, list 2. You're going to erase whatever is there from before. So a quick way to erase is that you go to L1, press clear, enter. Over here the same thing, you go up, press clear, then enter, boom. So now you can go plugging in, right? So let's remember this one is going to be L1, this one's going to be L2. So for L1 you're going to put 4, 3, 6, 5, 7, 2, 8, 1. And for the next one, you're going to have 2, 4, 8, 3, 5, 6, 7, 1. And so as you can see, for example, this one goes with this one. It makes sense. This 8 goes with that 7, which makes sense. This 2 goes with that 6, which makes sense. All right, you want to make sure that from that angle, it all makes sense, okay? So once you do that, well, I told you go to stat line reg, okay? Stat line reg, I need you to associate it to R value. Okay, stat line reg is for an R value, in this case for the correlation coefficient. All right, so you're going to go to stat, calculate, and reach line reg. It's a regression, okay, line reg. All right, cool. So line reg, your X list is going to be L1, perfect. Your Y list is going to be L2, perfect. Your frequency list, do you have one? You don't, so you're going to leave it empty, all right? A lot of people feel like you have to plug something into all of these things. Not necessarily. If your calculator lets you scroll down, then you don't have to plug in something, okay? And in this case, there is no frequency list, so you're not going to put anything, you skip it. For store reg EQ, for our interests, you're pretty much never going to do it. But if you ever want to graph, like this green line that I'm putting here, if you ever want to graph it, at this step, you can press alpha trace and put it into your y equals, okay? So into your y equals, it will go into y1 or into your y5, whatever you want, okay? We don't really care about that, so we're just going to do line reg normally and press calculate. And so from here, boom, you have your R value. Now, I'm sure some of you are thinking, dude, what the hell? Like, my calculator doesn't show my R value. Like, this guy's cheating, dude. Like, his emulator's, like, hacked or something. Like, what the heck? Nuh-uh. your calculator is always going to do what it asks it to be done. All right, it's a robot. And as long as artificial intelligence doesn't take over us, this calculator will do as we say. And so if you are not getting an R value, that means that you need to go to mode. So you press mode, and we're very used to having to change radian to degree or degree to radian for using sine or cosine or tangent, all right? But another thing that maybe doesn't get spoken about enough is that down here, you have this thing called stat diagnostics, okay? If it's off, you probably had this happen to you. No R value. And if it's on, you're going to see that now you do get an R value. And so there is no reason to have this on off. Might as well always leave it on. If you ever reset your calculator, make sure you turn it on. There is your R value. Okay, so for part B, which, I don't think I ever mentioned it, but for part B, that you need to calculate the value of Spearman's rank correlation coefficient. And there it is. So R is going to be 0.595238. And if you count significant figures, you're going to count 1, 2, 3. Do you round it up or keep it the same? You keep it the same. So if you want to do significant figures, it's 0.595. All right. So pretty easy 2 points. I don't think it's that hard. And this procedure is something you can memorize. Okay? So that is nice. Anyways, we keep going. We have that Thurston believes that artists with a higher number of social media followers sell more albums in the first week. And so he carries out a hypothesis test using a 10% significance level with the following null hypothesis. In the population, there is no monotonic relationship between the number of social media followers and the number of albums sold in the first week. And now we need to write down Thurston's alternative hypotheses. Now, a quick rule of thumb I can share with you right away is that HO is the not version of what you are trying to find, okay? And H1 is the not, which is the same as just positive, usually, okay, of what you're trying to find. Now let's remember, what is Thirsty Thurston trying to find? Thirsty Thurston believes that more popular musical artists sell more albums. And so what is the not of this? The not of this is that more popular musical artists don't necessarily sell more albums, okay? And that is why they say no monotonic relationship, which is just a very fancy way to say that there is no relationship, okay? So for HO, technically you would say no relationship between number social media followers and number albums sold in the first week, right? And because I told you that H1 is the not version of what you're doing, or just the opposite of HO, you can say that there is a relationship between number of social media followers and number of albums sold in the first week. Now, let's remember that Thirsty Thurston told us that he believes that more popular means more albums. And so to be very rigorous here, you would say that there is a positive relationship between number of social media followers and number of albums sold in the first week. So this is maybe a more intuitive way to explain it. HO is going to be the not version of what you're trying to find, and H1 is going to be the opposite of that. But if I get a little bit more hardcore mathematical with you, because you're in the IB, face it, you gotta get at least a little bit hardcore, all right? Technically, the HO, or the null hypothesis, okay, is something that is always going to state no change / no relationship, all right? The HO is always going to be like, nuh-uh, there's no effect, all right? The null hypothesis always assumes the status quo, that nothing is happening, okay? While the H1 says, the alternative hypothesis is saying, there is a change, girl, all right? Or there is a relationship. It's not just a fling. Oh my god. Okay, sorry. I'm just trying to be funny. So, for H1, there is a change. There is a relationship. It's not just a situationship, all right? And so, for H1, like, there is a relationship, there is something happening. Okay, H0 is always going to be there is nothing happening. H1 is there is something happening. The hard part is to understand, is it a positive something happening or a negative something happening? And because Thurston initially said more popular means more albums, you have to put the keyword positive. Okay? And so HO is no relationship. H1 is that there is a positive relationship. Okay? That is for part C. Not that hard. It's just understanding the intuition between HO and H1. All right? Then they tell you that the critical value of RS for this test is 0.643, and to state the conclusion of the hypothesis of the test, giving a reason. Now, part D, is actually very easy, but you need to understand what is going on, okay? Because on the one hand, I can just tell you, okay, so you got 0.595 from part B for your R value. This is less than 0.643, and so that means that there is insufficient evidence to reject HO. And so I can tell you this, I'm going to tell you to memorize it, and you're going to get those 2 points for free, okay? But we need to understand a little bit better, like, what is happening, okay? And so you can cut the video off here and say, okay, I can memorize this, nobody cares. Or you can say, I care a little bit, I want to understand a little bit what's going on, here I go, okay? So on the one hand, you got a value for RS, okay? We got a value for RS that was R equals 0.595, all right? And they tell you that the critical value of RS is 0.643. Now, some of you might be thinking, where did this critical value come from? And your critical value is always going to come from the 10% significance level, okay? And so this is a whole test that happened behind the scenes. I'm not sure if it was chi-squared or t-test, probably chi-squared. But anyways, there's this whole sort of process that depending on your significance level, you have a certain critical value. And why do they call it a critical value? Because if you are above this critical value, then you reject HO. If you are not above this critical value, then you fail to reject HO. What is another way to look at it? If you are above this critical value, then there is a change, okay? And if you're below this critical value, then there is no change. So think about it this way. They tell you that the critical value of RS for this test is 0.643. So that means for the correlation, they are asking for a correlation that is at least of an R of 0.643. And so because we got an R that was a little bit below that, around here, they're going to say, I get it. It's a positive correlation, but it's weak. It's not strong enough. And you say, okay, what is strong enough? Strong enough is 0.643. Strong enough is my critical value. So if you have an R value that is stronger than your critical value, stronger than this sort of minimum that they're asking for, then yeah, you would say, okay, there's valid evidence that Thurston was correct. But in this case, Thurston was incorrect because the R value he got was below the critical value, okay? And this critical value can change depending on the significance level that is asked for, okay? So in this case, we had to relate the actual value we got to the critical value. In other scenarios, you gotta compare the p-value to the significance level, okay? But in this case, we don't do that because we get the actual values, okay? Think about the significant level and the p-value as sort of like probabilities or percents and stuff like that. And in this case, you're literally just comparing values, okay? Like you're comparing the critical value of RS to the value of RS that you got. And so because 0.595 is lower than the correlation that they were asking for, you say, okay, my evidence is not strong enough, so there is insufficient, I don't know why I put insufficient, there is insufficient evidence to reject HO, which another way to think about it is that you accept HO. And let's remember that HO was no relationship / no change. And so that means that you accept that there is no relationship between amount of media followers to albums that are sold. So Thurston, unfortunately, better dedicate himself to drinking water because this guy got it wrong over here. Just kidding. Just because you get something wrong doesn't mean you should give up. True failure comes by giving up. That is my honest opinion. In most cases, I would say. Anyways, part D is that. As long as you state this and then give a little bit of a line saying insufficient evidence to reject HO, you're going to get full credit. Ladies and gentlemen, that is for part D and for the whole test for number 12, actually. So I hope it helped. And yeah, I'll see you around.